Picture the universe as it was in its earliest youth, a vast sea of darkness, thick and impenetrable. For hundreds of millions of years after the Big Bang, there were no stars, no galaxies, not even a single point of light to pierce the endless, neutral fog of primordial gas. The cosmos was a silent, opaque void, a shadowy canvas waiting for its first brilliant strokes of creation. This was the universe before its great awakening, a state of profound quiet that would not last. Then something incredible happened. A transformation began, so immense and powerful that it fundamentally changed the nature of reality itself, ripping apart the very fabric of that neutral fog and flooding the cosmos with light. This pivotal moment, this cosmic revolution, is what we call the Cosmic Reionization Era, and it marks one of the most profound and mysterious chapters in the entire history of our universe. What could possibly cause such a fundamental shift? How did our universe journey from that formless dark into the sparkling, transparent expanse we gaze upon today? This era represents a cosmic dawn, a bridge between the simple, hot beginnings of the Big Bang and the complex, structured universe of galaxies we inhabit now. It was during this time that the first stars and galaxies flickered to life, their intense radiation burning away the fog, ionizing the hydrogen gas that filled all of space and ultimately clearing the void for light to travel freely across billions of light years. We are only just beginning to piece together this epic story, a narrative written in the faintest whispers of ancient light, and every new discovery seems to reveal more questions than answers. Today, we are embarking on a journey to the very edge of known physics and observable time to explore 25 of the most profound mysteries surrounding the Cosmic Reionization Era. We will confront the enigmas that keep astrophysicists awake at night, questions about the nature of the very first stars, the role of supermassive black holes, and whether we are missing entire pieces of the cosmic puzzle. This is not just a story about the past, it is a detective story about our own origins, a quest to understand how a dark, empty universe became a place capable of giving rise to us. So let's dive into the deep unknown and uncover the secrets of this cosmic rebirth, a time when everything changed. Our first great mystery takes us to the very beginning of star formation, to a type of object so ancient and elusive that no telescope has ever directly seen one. These are the population 3 stars, the universe's very first generation of stellar giants. To understand why they are so mysterious, we have to understand the pristine environment they were born into. In the early universe, there were no heavy elements, no carbon, no oxygen, no iron. The only materials available were the primordial elements forged in the Big Bang itself: hydrogen, helium, and a trace amount of lithium. This simple chemical recipe had a profound consequence. Without heavier elements to help the cosmic gas clouds cool down and fragment efficiently, these first stars could accumulate absolutely staggering amounts of mass. Current theories suggest they weren't just large, they were behemoths potentially containing the mass of several hundred of our own suns packed into a single, ferocious ball of nuclear fire. The life cycle of such a star is almost unimaginable to us. With that much mass driving immense pressure and temperature at their cores, they burn through their nuclear fuel at a breathtaking, profligate rate. They would have shone with a fierce, brilliant blue-white light, emitting enormous amounts of high-energy ultraviolet radiation. This radiation is the key that begins to unlock our main story. It was this intense UV light that started to rip electrons away from the neutral hydrogen atoms that filled the cosmos, beginning the slow, epoch-long process of reionization. But this brilliance came at a terrible cost. A star that lives so intensely cannot last. Their lifetimes were cosmically brief, perhaps only a few million years, a mere blink in the multi-billion-year history of the universe before they met spectacular, cataclysmic ends in supernova explosions of unprecedented power. These violent deaths served a crucial purpose, however, seeding the surrounding gas with the first heavy elements, which would eventually go on to form the more long-lived, smaller stars we see today, the population 2 and population 1 stars that fill our modern galaxy. This brings us to the core of the mystery. If these population 3 stars were so pivotal, so fundamental to everything that came after, why can't we find any? The answer is painfully simple: they are all gone. They lived fast, died young, and left no survivors. We are, in effect, trying to solve a cosmic murder mystery where the perpetrators and the victims have completely vanished, leaving behind only indirect clues and a transformed crime scene. Our entire understanding of them comes from sophisticated computer simulations and from hunting for their chemical fingerprint in the atmospheres of the most ancient stars we can see. It's like analyzing the composition of soil in a very old forest to infer what the very first trees must have been like, long after those original trees have turned to dust. Finding direct, observational evidence for a population 3 star remains one of the single greatest holy grails in all of modern astronomy, a discovery that would allow us to look directly upon the face of one of the universe's very first architects. And so we arrive at a second, equally profound puzzle, one that is intimately connected to the fate of those first stars, the nature of the very first galaxies. If population 3 stars were the pioneers, then the first galaxies were the settlements they built, the cosmic structures that assembled these brilliant but short-lived beacons into organized communities. For a long time, our theoretical models painted a fairly straightforward picture. We expected that the earliest galaxies would be relatively small and faint. They would be what astronomers call dwarf galaxies, humble collections of gas and stars, gradually merging and clumping together over billions of years to form the majestic spirals and ellipticals we see in the modern universe. In this slow and steady scenario, reionization would have been a drawn-out process, driven by the collective, gentle output of countless faint early galaxies. But the universe, it seems, loves to surprise us. When the James Webb Space Telescope began its unprecedented infrared gaze into the deep past, it didn't just see those expected faint, infant galaxies. It saw giants. It captured light from galaxies that existed when the universe was only a few 100 million years old, a mere toddler in cosmic terms, and these galaxies appeared shockingly massive, bright, and mature. They were fully formed cosmic cities at a time when we expected only small villages. This discovery has sent shockwaves through the field of cosmology, fundamentally challenging our most cherished models of how structure forms in the universe. How could such immense galaxies assemble their vast amounts of stars so quickly, so soon after the Big Bang? It's as if archaeologists digging in a layer of Earth they believed corresponded to the Stone Age suddenly unearthed a gleaming modern skyscraper. It forces us to ask, did galaxy formation get a much faster, more energetic start than we ever thought possible? This mystery is not just about size and brightness, it's fundamentally about power. The key actor in the reionization drama is the ionizing photon, a packet of ultraviolet light with enough energy to strip an electron from a hydrogen atom. The earliest galaxies were the primary factories for producing these photons, but the type of factory matters immensely. Were they powered by the ferocious, short-lived population 3 stars, generating a torrent of ionizing radiation but then quickly going supernova? Or were they dominated by more stable, longer-lived but less intensely powerful smaller stars? The answer dictates the entire timeline and texture of the reionization process. A universe lit by countless small, faint galaxies would have reionized the cosmos slowly and patchily, like a slow sunrise gradually burning off a morning fog. A universe dominated by a smaller number of brilliant, massive galaxies would have done the job much more aggressively, like a series of sudden, powerful flashbangs igniting and clearing vast bubbles of transparent space all at once. The James Webb Space Telescope is now our chief detective in this cosmic investigation. Its unparalleled ability to see in infrared light allows it to look straight through the dust of time and capture the stretched, reddened light from these earliest galactic building blocks. With every new deep field image, it is not just finding galaxies, it is taking a census of the ancient universe. By counting them, measuring their brightness, and analyzing their light to understand their chemical composition and the ages of their stars, Webb is providing the first hard data from this frontier era. The emerging picture is complex and wonderfully messy. It suggests that the infant universe was a place of incredible diversity, with both faint, small galaxies and unexpectedly bright, massive ones coexisting. This means the process of reionization was likely not a simple, uniform event, but a chaotic and uneven transition, with different parts of the universe becoming transparent at different times, driven by different kinds of galactic engines. The puzzle of the first galaxies is forcing us to rewrite the story of cosmic dawn, revealing a narrative that is far more dynamic and explosive than we ever imagined. The discovery of these surprisingly bright and massive early galaxies throws a fascinating new variable into one of the most fundamental debates in modern cosmology. What exactly provided the overwhelming majority of the energy that ripped the universe apart? This is the mystery of the primary drivers of reionization, and it pits two cosmic powerhouses against each other in a theoretical battle for the ages. On one side, we have the stellar populations of early galaxies, the collective ultraviolet fury of billions upon billions of hot, young stars. On the other, we have the most violent and efficient engines in the universe, the supermassive black holes that lurked at the centers of many of those same galaxies, powering brilliant, beacon-like objects known as quasars. For a long time, the intuitive and leading candidate has been starlight. Picture a vast early galaxy filled with immense nurseries of bubbling gas giving birth to countless new stars. Many of these stars, particularly the hottest and most massive ones, flood their surroundings with a torrent of high-energy ultraviolet photons. Each of these photons is a tiny bullet capable of striking a neutral hydrogen atom and liberating its electron, transforming it from an opaque barrier into a transparent ionized plasma. The appeal of this stellar model is one of sheer numbers. If there were enough galaxies filled with enough stars, their cumulative, steady output could, in theory, provide the colossal energy required to reionize the entire cosmic medium. It's a democratic model where the work is done by the collective effort of countless stellar furnaces. But then we have the quasars. A quasar is born when a supermassive black hole, an object with the mass of millions or even billions of suns, is actively feeding on vast quantities of gas, dust, and even entire stars from its surrounding galaxy. As this material spirals inward at near light speed, it forms a searingly hot, bright disk of plasma around the black hole. The gravitational energy released in this frantic feast is staggering, converting matter into radiation with an efficiency dozens of times greater than nuclear fusion in a star. A single, brilliant quasar can outshine its entire host galaxy, and its light is not just optical and ultraviolet. It floods space with an intense barrage of even higher energy X-rays. This makes it a uniquely potent and penetrating ionizing source, capable of clearing out huge, spherical bubbles in the neutral hydrogen fog over immense cosmic distances. The challenge for astronomers is quantifying the contribution of each. It's not a simple either slash or question, but a complex cosmic accounting problem. Imagine trying to figure out whether a large city was lit primarily by countless household light bulbs or by a few dozen immensely powerful stadium floodlights. You'd need to count all the bulbs, measure all the floodlights, and determine how much illumination each one provides to the total city glow. That's precisely the task facing cosmologists, but for a city the size of the observable universe, and using only the faint, ancient light that has taken over 13 billion years to reach us. The James Webb Space Telescope is our ultimate tool for this cosmic census. peering back to count the faintest, most numerous star-forming galaxies and to identify the brilliant but rare quasars from this epoch. Initial evidence points toward a nuanced answer. While quasars are undeniably powerful, they also appear to have been relatively rare in the early universe. They are the cosmic equivalent of flashbangs, brilliant and capable of creating large, isolated ionized bubbles, but perhaps too few and far between to be responsible for the entire uniform process. The collective output from the vast populations of faint, early galaxies seems to be the more likely workhorse, providing the steady, pervasive background radiation that did the bulk of the heavy lifting. However, the recent discovery of more massive, brighter than expected early galaxies complicates this picture, as they could have hosted more powerful black holes and produced a much stronger stellar ionizing output than our models predicted. It's possible that reionization was a team effort, led by starlight, but with quasars playing a crucial, specialized role in punching through the densest regions of gas or in triggering star formation in neighboring galaxies, creating the complex, patchy pattern of ionization that we are beginning to detect. Getting this balance right is absolutely crucial because the dominant energy source sets the clock for the entire reionization era. If it was mostly starlight, the process was likely more gradual. If quasars played a larger role, it could have been more rapid and explosive. The answer is written in the faint afterglow of the Big Bang and the ancient light of the first celestial structures, and we are only now learning how to read it. But trying to pinpoint the exact chronology of this cosmic dawn is like trying to time a sunrise happening in slow motion across a billion years. We know the universe started out opaque and ended up transparent, but the when and how long of that transformation form one of the most crucial puzzles in modern cosmology. Did the lights flicker on all at once in a brilliant, dramatic flash, or was it a slow, stately dawning that gradually brightened the cosmos? The evidence we have paints a fascinatingly complex and sometimes contradictory picture. Our most powerful clue comes from the oldest light we can see, the cosmic microwave background radiation. This is the remnant glow from the Big Bang itself, a snapshot of the universe when it was just 380,000 years old, long before the first stars. By studying the subtle polarization patterns in this ancient light, satellites like the Planck Observatory have been able to deduce when the bulk of the reionization process was finished. The data suggests that by the time the universe was about 1 billion years old, the vast majority of the neutral hydrogen had been split apart. This gives us a firm end date, a cosmic finishing line. But this measurement is like an archaeologist finding a city that was clearly inhabited by a certain date. It tells you when the city was fully built, but it doesn't tell you how long the construction took or when the first foundations were laid. To understand the beginning and the pace, we have to look at a different kind of fossil, the light from the most distant quasars. As their brilliant beams travel across the universe towards us, they pass through immense clouds of the intergalactic medium. By analyzing the absorption lines in a quasar's spectrum, essentially the specific shadows cast by neutral hydrogen gas along the line of sight, we can create a map of the universe's opacity at different distances and therefore different times. When we look at quasars from when the universe was around 900 million years old, their light shows very few of these hydrogen absorption lines, confirming that the space between galaxies was largely transparent by then. But when we push our observations back to quasars from just 700 or 800 million years after the Big Bang, the story changes dramatically. Their light is heavily absorbed, revealing that they are shining through a thick, pervasive fog of neutral hydrogen. This tells us that reionization was still very much underway at that point. This is where the mystery deepens, because these two different methods seem to be telling slightly different stories about the duration of the process. The quasar data suggests a relatively late and rapid reionization, one that kicked into high gear around 750 million years after the Big Bang and finished in a cosmically swift 200 to 300 million years. It's a punctuated equilibrium model where a long, quiet period of building potential finally gives way to a violent, rapid transformation. However, other observations, particularly of the very faintest and earliest galaxies now being spotted by the James Webb Space Telescope, hint at a different possibility. If these small, numerous galaxies started forming stars much earlier than we thought, they could have begun the ionization process much more gradually, creating small, isolated bubbles of transparency that only slowly grew and merged over a much longer period, perhaps starting as early as 200 or 300 million years after the Big Bang and stretching out for nearly 500 million years. This would be a slow burn model, a prolonged cosmic dawn rather than a sudden flash. So, which timeline is correct? Was it a swift revolution or a slow evolution? The growing consensus is that the truth likely lies in a messy middle ground. Reionization was almost certainly not a uniform, synchronized event across the entire cosmos. Picture a vast landscape on a foggy morning. The sun doesn't burn off the fog everywhere at once. First, the hilltops clear as the sun hits them, creating isolated clearings. Then, the valleys gradually follow. In the cosmic context, the densest regions of the universe, where the first galaxies and quasars clustered, would have ionized their surroundings first, creating vast, growing bubbles of transparent space. Meanwhile, the more barren cosmic voids would have remained filled with neutral fog for much longer. The timeline we measure depends entirely on which part of this patchy, uneven process we are observing. The cosmic microwave background gives us the global average, the moment when the last stubborn patches of fog finally evaporated. The quasars give us a view along specific, perhaps already cleared, lines of sight. And the faint galaxies show us the early, decentralized efforts that started the whole process. Reconciling these different perspectives into a single, coherent timeline is one of the primary goals of next-generation observatories, as the precise duration of reionization holds the key to understanding the true nature and power of the universe's very first sources of light. But what did this cosmic fog actually look like? Was it a perfectly uniform shroud, an even and featureless veil of neutral hydrogen extending in all directions, or was it something far more complex and textured? This brings us to our fifth mystery, the distribution of the neutral hydrogen itself. Understanding its structure is key to visualizing the reionization process because it dictates whether the universe cleared in a smooth, uniform fade, like a single light brightening a room, or in a chaotic, patchy process of growing bubbles, like air holes forming and merging in a sheet of ice. The answer dramatically changes our mental image of cosmic dawn. For a long time, the simplest assumption was that the early universe's gas was fairly smooth and evenly distributed, a relic of its incredibly hot, dense beginnings. In this model, as the first stars and galaxies ignited, they would have begun to ionize their immediate surroundings, creating small, spherical pockets of transparency. These ionized bubbles would then slowly grow and eventually merge with others, like soap suds coalescing on the surface of water, until the entire universe was connected in a single, vast, ionized medium. This bubble model suggests a gradual but highly uneven transition, where any given point in space could be either completely opaque or perfectly transparent, depending on its proximity to the nearest brilliant source of light. The universe would have looked like a cosmic Swiss cheese, with the ionized bubbles representing the holes. However, other theories propose that the process might have been even more lumpy and discontinuous. Perhaps the distribution of neutral hydrogen was itself incredibly clumpy from the start, not a uniform fog but a landscape of dense clouds and vast, empty voids. In this scenario, the first light would have easily flooded the empty voids, creating massive, irregularly shaped transparent regions, while the dense clouds of gas acted as stubborn, long-lasting bastions of neutrality, resisting ionization for much longer. This would make reionization a highly inefficient and protracted battle, where clearing the last 10% of the neutral gas could have taken as long as clearing the first 90%. The challenge for cosmologists is that we cannot see this structure directly with optical telescopes. We need a completely different kind of eye, one tuned to a very specific and ancient signal. This is where one of the most elegant tools in all of astronomy comes into play, the 21 centimeter line. The physics behind it is beautifully simple. A neutral hydrogen atom consists of a single proton and a single electron. Both of these particles have a property called spin. Think of them as tiny magnets that can be aligned in the same direction or in opposite directions. It takes a tiny bit more energy for the electron and proton to have their spins aligned than to have them opposite. When a hydrogen atom's electron spontaneously flips its spin to align with the proton, it releases that tiny bit of excess energy as a photon of radio waves with a very specific wavelength, 21 centimeters. Every single neutral hydrogen atom in the universe is capable of emitting this faint whisper. During the Cosmic Reionization Era, before the first stars lit up, the entire cosmos was filled with this gas, meaning it should have been glowing softly with a uniform radio hum at the 21 centimeter wavelength. But as the first sources of light began to turn on, they did two things to this signal. First, their intense ultraviolet radiation heated the surrounding gas, making it slightly more energetic. Second, and more importantly, as they ionized the hydrogen, they ripped away the electrons, destroying the very atoms capable of producing the 21 centimeter signal. So, as reionization progressed, the smooth background hum of 21 centimeter radiation would have begun to develop complex patterns. Regions around the first galaxies and quasars would have first brightened as the gas was heated, and then gone completely silent as the hydrogen was ionized and the signal vanished. The result would be a cosmic map of incredible detail, evolving charts showing the precise locations of the neutral gas and the growing voids of ionized plasma. By observing the 21 centimeter signal from different cosmic epochs, we could, in theory, watch a time-lapse movie of the reionization process itself, observing the bubbles of transparency as they are born, grow, and finally merge to clear the entire cosmic fog. The promise of this technique is nothing short of revolutionary, but the reality of detecting this signal is one of the most formidable technical challenges modern science has ever faced. The 21 centimeter light from the early universe has been traveling for over 13 billion years to reach us. In that time, the expansion of the universe has stretched the wavelength from 21 centimeters to several meters, pushing it deep into the long wavelength radio part of the spectrum. This signal is incredibly faint, millions of times weaker than the barrage of radio noise from our own galaxy, from earthly sources like radio stations and satellites, and even from the atmosphere itself. Detecting it is like trying to hear a single snowflake land in the middle of a rock concert. To overcome this, astronomers are building vast, revolutionary radio telescopes in some of the most remote locations on Earth, places like the deserts of South Africa and the outback of Western Australia, where the radio silence is as profound as humanity can make it. Arrays like the Hydrogen Epoch of Reionization Array and the Square Kilometer Array are not single dishes but thousands of simple radio antennas spread across hundreds of kilometers, working in concert to digitally sift through the cosmic static and isolate the faint, telltale pattern of the primordial hydrogen. They are not trying to take a pretty picture, they are performing the most sensitive auditory archaeology imaginable, listening for the echoes of the universe's first great transformation. Yet for all the power of stars and quasars, there was an invisible hand guiding the entire show, a silent partner in the cosmic drama of reionization that we cannot see, but whose gravitational influence was absolutely paramount. This brings us to our sixth profound mystery, the enigmatic role of dark matter. To understand how the first sources of light could even form, we have to look beyond the regular atoms that make up everything we can touch and see. We have to venture into the realm of the cosmos's hidden architecture. Dark matter, which does not emit, absorb, or reflect any light, makes up about 85% of the matter in the universe. Its presence is felt only through its immense gravitational pull, and in the early universe, that pull was the fundamental force that drew the primordial gas together, creating the gravitational wells where the first stars and galaxies were born. Without dark matter acting as a cosmic skeleton, the ordinary matter, the hydrogen and helium gas would have been too thinly spread and moving too quickly to ever collapse into the dense clumps required to ignite nuclear fusion. The luminous actors of reionization were merely playing out their roles on a stage built almost entirely by dark matter. The leading theory, known as the cold dark matter model, paints a very specific picture of how this unfolded. In this scenario, cold means the dark matter particles were moving relatively slowly in the early universe. This slowness was crucial. It allowed tiny, random quantum fluctuations in the density of the dark matter, stretched to cosmic scales by the initial rapid expansion of the universe, to begin clumping together gravitationally first. These clumps acted as seeds, attracting more and more dark matter, growing over hundreds of millions of years into a vast, invisible cosmic web, a network of dense filaments connecting at massive nodes with enormous voids in between. It was onto this pre-existing, invisible scaffolding that the neutral hydrogen gas flowed. The gas, feeling the gravity of the dark matter, settled into these wells, cooling and condensing until it was dense enough to fragment and form the very first stars and protogalaxies. In this view, reionization was a process that unfolded along the filaments and hubs of the dark matter web, with the first light switching on in the densest regions first, then gradually spreading outwards. However, the cold nature of dark matter is not a settled fact, and this is where the mystery deepens considerably. What if dark matter wasn't cold but was instead warm? Warm dark matter would consist of particles moving at a significant fraction of the speed of light in the early universe. This higher velocity would have a dramatic effect, effectively smoothing out the smallest clumps of dark matter. The cosmic web would still form, but it would be far less detailed, lacking the countless tiny, dense halos that the cold dark matter model predicts. This distinction isn't just a minor technicality, it has profound consequences for the timeline of reionization. In a universe dominated by cold dark matter, a vast number of small, faint dwarf galaxies would form first, potentially starting the reionization process very early, even if each one was only a feeble ionizing source. It would be a bottom-up approach with small structures merging to form larger ones. But in a warm dark matter universe, the formation of the very first galaxies would be delayed because the small-scale seeds for them are wiped out. The first objects to form would be larger and more massive from the outset. This would mean a later, but potentially more explosive, start to reionization, as these bigger galaxies would turn on with a much greater collective brilliance. This theoretical debate is now being tested against real observations from our most powerful telescopes. The James Webb Space Telescope's discovery of those surprisingly massive and bright early galaxies presents a fascinating challenge to both models. On one hand, their mere existence so early in time suggests that galaxy formation can indeed proceed with incredible speed, which might seem to favor the efficient, bottom-up clustering of cold dark matter. On the other hand, if we are finding these large galaxies but a distinct lack of the predicted swarms of accompanying small dwarf galaxies from that same epoch, that could be a hint that the warm dark matter model has some merit, as it naturally suppresses the formation of those smallest structures. Astronomers are now engaged in a cosmic census, desperately trying to count the numbers of the faintest, smallest galaxies in the early universe. The final tally will be a crucial piece of evidence. A universe teeming with ancient dwarf galaxies would bolster the cold dark matter hypothesis, while a scarcity of them would force us to seriously consider that dark matter is warmer, and thus that the story of cosmic structure formation, and by extension reionization, needs a significant rewrite. The properties of this invisible substance, determined by physics far beyond the standard model, may have set the rules for the entire reionization era, dictating when the first lights could appear and how they were distributed across the cosmos, making dark matter the ultimate puppet master of the cosmic dawn. Even if a galaxy is teeming with billions of scorching hot stars, producing a veritable flood of ionizing radiation, that energy is useless for the grand project of cosmic reionization if it can't escape its own home. This brings us to a deeply technical yet profoundly important puzzle, the escape fraction. This is the term scientists use for the tiny, critical percentage of ionizing photons that actually manage to leak out of a galaxy and travel into the vast intergalactic medium to rip apart the neutral hydrogen fog. Think of an early galaxy not as a simple light bulb, but as a brilliantly lit building shrouded in a thick, internal haze of gas and dust. Most of the light gets trapped and absorbed inside, heating up the local environment. Only the photons that, by pure chance, travel through a rare, clear pathway, a fortuitous tunnel, or a gap in the cosmic clouds, can actually escape to shine on the outside universe. For reionization to work, these escape routes had to be common, and that single number, the escape fraction, holds immense power. If it was just a few percent, then early galaxies would have been pathetically inefficient, and we'd need a staggering number of them to account for the ionization of the entire cosmos. But if it was 10, 20, or even 50%, then the job could have been done by far fewer, far more powerful sources. Measuring this escape fraction today is one of the most frustrating challenges in observational astronomy. The reason is simple. The very same neutral hydrogen that filled the early universe also exists in copious amounts inside every galaxy. These internal clouds of gas are perfect sponges for the high-energy ultraviolet light we need to detect. By the time this light has fought its way through its own galactic home, its signature is severely diminished, if not completely erased. Compounding the problem, the intergalactic medium itself, even after reionization, still contains enough leftover neutral hydrogen to absorb a great deal of this radiation over billions of light-years of travel. So, by the time the faint whisper of this escaped light reaches our telescopes, it is incredibly difficult to separate from the glare of the galaxy's lower energy, non-ionizing light. It's like trying to measure the precise amount of water vapor escaping from a steaming pot by studying the cloud of steam from a mile away, while the pot itself is sitting in a dense fog bank. So what physical conditions inside a galaxy would allow for a high escape fraction? It likely requires a perfect and rather violent storm of factors. First, the galaxy needs to have a very porous interstellar medium. Instead of a smooth, dense cloud of gas, it needs to be filled with bubbles and channels, perhaps carved out by the intense stellar winds and powerful supernova explosions from previous generations of massive stars. These explosions can literally blow the roof off the galaxy, punching holes in the gas and creating low-density chimneys through which ionizing radiation can stream freely. Second, the galaxy might need to be relatively low in metals, the astronomers' term for elements heavier than hydrogen and helium. Dust grains, which are made of these heavier elements, are fantastically efficient at absorbing ultraviolet light. In the very earliest, most pristine galaxies, before supernova had time to pollute the environment with dust, the interstellar medium may have been far more transparent to these crucial photons. This suggests that the most efficient ionizing engines in the universe might not have been the brightest or most massive galaxies, but perhaps the smaller, purer, and more violently energetic ones, where star formation was a chaotic, explosive process that continuously disrupted the gas and cleared avenues for light to escape. The quest to pin down a definitive value for the escape fraction is driving some of the most cutting-edge work with the James Webb Space Telescope. Astronomers aren't just looking at galaxies, they are trying to perform a kind of cosmic autopsy on their internal structure. By analyzing the spectral lines of hydrogen and other elements, they can infer the density and motion of the gas inside these distant systems. In some cases, they look for the telltale signature of gas that is flowing outward in a tremendous wind, a galactic-scale hurricane that could be the very process that is clearing a path for the ionizing radiation. Early results are intriguing but also deeply puzzling, showing a huge variation from galaxy to galaxy. Some systems show virtually no sign of escaping ionizing photons, while others appear to be remarkably leaky. This variability itself is a crucial clue, hinting that the process of reionization was not driven by a uniform army of identical galaxies, but by a diverse cast of characters, each contributing differently to the cosmic effort based on its own unique history of star formation, mass, and internal structure. The great mystery of the escape fraction forces us to look past the simple birth of light and into the complex, dynamic, and often self-destructive lives of the galaxies that housed it. While dark matter set the stage and galaxies built the structures, the real action, the transformative violence that both built and destroyed the environments for reionization, came from the spectacular deaths of the universe's first stars. We've already touched on the supernova explosions that ended the brief lives of the massive population 3 stars, but to understand their true impact, we must look beyond their role as mere recyclers of chemical elements. These cataclysms were not just an endpoint, they were a fundamental feedback mechanism, a cosmic force of both creation and destruction that directly shaped the pace and pattern of the universe's great illumination. The relationship between these early supernova and the reionization process is a perfect example of a cosmic paradox, where the same event could simultaneously advance and hinder the clearing of the cosmic fog, depending on the context. First, let's consider the constructive side of this explosive feedback loop. An early galaxy is a dense, gaseous environment. For ionizing photons to escape, they need a clear path out, but the very gas that forms stars also traps their light. This is where a supernova becomes a cosmic landscaper. When a star hundreds of times the mass of our Sun explodes, it does so with almost unimaginable energy, ejecting its outer layers at speeds of thousands of kilometers per second. This blast wave slams into the surrounding interstellar gas, sweeping it up like a cosmic plow and pushing it outward. The result is the creation of a vast, low-density cavity, a superbubble within the galaxy. Imagine a bubble rising through a thick liquid. It clears a temporary tunnel as it moves. In a galactic context, these supernova-blown bubbles could carve out chimneys and tunnels through the dense gas, creating the crucial escape routes that allowed the ionizing ultraviolet light from subsequent generations of stars to stream out into intergalactic space unimpeded. In this way, the violent death of one generation of stars directly enabled the light of the next generation to contribute more effectively to reionization. It was a form of cosmic self-sacrifice, where a star's death cleared the way for the light of its stellar descendants to travel farther and do more work on a cosmic scale. Furthermore, these explosions were the primary agents for the second key constructive process, chemical enrichment. The universe began with only hydrogen, helium, and a trace of lithium. Every other element in the periodic table, from the carbon in our cells to the oxygen we breathe and the iron in our blood, had to be forged in the nuclear furnaces of stars and then scattered into space. The first supernova were the ultimate origin points for this cosmic pollution. They blasted newly synthesized heavy elements, what astronomers call metals, far out into the primordial gas. This enrichment had a profound and counterintuitive effect on future star formation. While it might seem that adding new elements would always be beneficial, it actually changed the fundamental rules of the game. In a pristine, metal-free gas cloud, the only way to cool down and collapse is through the relatively inefficient emission of light from hydrogen molecules. But when you add even a tiny amount of heavier elements like carbon and oxygen, the gas suddenly has many more and far more efficient ways to cool. This more efficient cooling allows the gas to fragment into smaller, denser clumps. Instead of forming only monstrous 200 solar mass behemoths, enriched gas clouds can form a whole spectrum of stars, including many smaller, longer-lived stars like our own Sun. This shift is critical because while the massive stars produce the most ionizing photons, they live and die too quickly. A population that includes more stable, long-lived stars provides a steadier, more sustained source of ionizing radiation over billions of years, potentially contributing to a more prolonged and stable reionization process. However, this constructive power came with an equally potent destructive capacity, and this is where the paradox deepens. The same supernova blast that can clear a path for light can also be devastatingly effective at shutting down the very star formation that powers reionization. Picture one of the universe's first small proto-galaxies, a fragile collection of gas held together by a tiny dark matter halo. It begins to form its first cluster of massive stars. Within a few million years, these stars go supernova. If the galaxy is small enough with a relatively weak gravitational pull, the combined energy of multiple supernova can be catastrophic. The blasts can overwhelm the galaxy's gravity, violently expelling not just the gas immediately around the stars, but a significant fraction of the galaxy's entire gas reservoir. This process, known as supernova feedback, can literally blow a galaxy apart. The raw material for future star formation is hurled out into intergalactic space, leaving the galaxy starved and dormant. For a time, that galactic engine of reionization is switched off. It's as if a fledgling factory, just starting production, had its entire supply of raw materials and its power source simultaneously destroyed by the waste products of its first successful run. In this scenario, supernova act as a regulatory brake, potentially delaying the progress of reionization by quenching the star formation in the smallest, most numerous galaxies, the very ones that might have provided the early, pervasive background radiation needed to start the process. So, did supernova help or hinder? The answer is almost certainly both, and the net effect depended on a delicate cosmic balance. The outcome hinged on the mass of the galaxy. In larger, more massive galaxies with stronger gravitational fields, the supernova explosions could not eject all of the gas. They would stir it up, create turbulent bubbles, and enrich it, but the galaxy would retain enough fuel to form new stars. In these more robust systems, supernova were a constructive, regulating force, creating escape routes and diversifying the stellar population without causing total collapse. But in the smallest, most fragile dwarf galaxies, supernova feedback could be a death sentence, effectively sterilizing them and postponing their contribution to the cosmic light show. This creates a fascinating picture of the reionization era, not as a uniform process, but as a chaotic competition between construction and destruction. Some regions of space would be illuminated early by galaxies that managed to survive their own violent births, while other regions might have fallen dark again after a brilliant first flash, their galactic lights snuffed out by the very explosions that gave them their first heavy elements. Understanding this complex feedback loop is key to modeling how reionization propagated through the cosmos, revealing a universe where death was as essential as life in the journey from darkness to light. Yet for all the brilliance of quasars and the surprising maturity of massive early galaxies, there is a compelling argument that the true heroes of the reionization era might have been the universe's most humble, diminutive citizens. This leads us to our ninth profound mystery, the potential dominant contribution of faint, low-mass galaxies. Picture the cosmic landscape not as a place dominated by a few glittering metropolises, but as an endless countryside teeming with countless tiny villages, each with a few modest lights. While any single one of these dwarf galaxies would have been incredibly faint, their sheer overwhelming numbers could have meant that, collectively, they provided the steady, pervasive background radiation that did the bulk of the work in burning away the cosmic fog. It's a classic case of strength in numbers, where the combined output of countless faint sources can easily outshine the most brilliant but rare beacons. The logic behind this idea is rooted in a fundamental principle of astronomy, the luminosity function. This is a statistical map of the universe that tells us how many galaxies exist at different levels of brightness. In almost every epoch we've studied, the rule holds true. For every one extremely bright galaxy, there are dozens of moderately bright ones, and for every one of those, there are thousands of incredibly faint, low-mass dwarf galaxies. It's a cosmic pyramid scheme with an immense base of tiny contributors supporting the entire structure. If this same distribution held true in the early universe, and there's every reason to believe it did, then the collective ultraviolet output from these countless faint dwarfs could have been the primary driver of reionization, a democratic cosmic effort rather than an aristocratic one led by a few brilliant overlords. There's another crucial reason why these small galaxies might have been particularly efficient ionizing engines. It goes back to the critical concept of the escape fraction, the percentage of ionizing photons that can actually leak out of a galaxy. Large, massive galaxies have deep gravitational potential wells and are often filled with vast, dense clouds of gas and dust, creating a formidable maze that traps ionizing radiation. But a tiny, low-mass dwarf galaxy has a much weaker gravitational pull. Its interstellar medium can be far more easily disrupted and made porous by the very first supernova explosions from its initial burst of star formation. In these fragile systems, powerful stellar winds and supernova blasts can literally blow away the entire gaseous envelope of the galaxy, effectively ripping the roof off and allowing the intense ultraviolet light from its hot, young stars to stream out into intergalactic space with very little obstruction. A small galaxy might be able to release a much higher fraction of its ionizing photons than a larger, more massive one that tends to hold onto its gas more tightly. So, while a single dwarf galaxy produces far fewer ionizing photons than a giant, it might be exponentially more efficient at putting every single one of them to work on the cosmic scale. The major problem and the heart of the mystery is that this vast population of faint pioneers is incredibly difficult to observe. Our most powerful telescopes, including the Hubble Space Telescope, have pushed to their absolute limits to detect the brightest galaxies from the reionization era. The countless faint dwarfs that must have existed lie far below this detection threshold, hidden in the noise. They form a kind of unseen majority, a cosmic dark matter in the realm of light. For decades, they have been a theoretical necessity, but not an observational reality. We have been trying to understand the economic output of an entire civilization by only studying its billionaires, completely missing the collective productive power of its entire middle and working class. This is precisely where the revolutionary capabilities of the James Webb Space Telescope are beginning to change the game. Webb's immense mirror and sensitive infrared instruments are designed to peer deeper and fainter than any observatory before it. It is not just looking for the brilliant giants, it is conducting a deep, systematic census of the cosmic populace, hunting for these faint, dwarf galaxies at the edge of time. Early results are already hinting that these populations are there, and they may be even more numerous than some models predicted. Every faint, red smudge that Webb adds to its tally is a potential piece of this puzzle. By counting them and estimating their collective brightness, astronomers can finally begin to run the numbers, to calculate whether their combined ionizing output was indeed sufficient to power the reionization of the universe. The implications of this mystery are immense. If the faint galaxies were the primary drivers, it paints a very different picture of how reionization unfolded across space and time. Instead of a process dominated by a few large, isolated ionized bubbles around brilliant quasars and massive galaxies, reionization would have been a far more uniform and gradual process. Imagine a foggy landscape where countless small campfires are lit simultaneously, each clearing a small patch of mist around it. Slowly, as these patches grow and merge, the entire fog bank dissolves in a steady, all-encompassing brightening. This model suggests a more gentle and prolonged dawn, one that was less about dramatic explosions of light and more about the patient, collective effort of trillions of unassuming stellar nurseries scattered across the infant cosmos. Resolving this mystery is not just about assigning credit. It is about understanding the fundamental character of the universe's transformation from darkness to light, and whether that transformation was led by the cosmic few or the countless many. But to truly grasp the mechanics of this great clearing, we have to venture into the seemingly empty voids between the galaxies, into the realm of the intergalactic medium itself. This was not a perfect vacuum. It was a diffuse, pervasive ocean of primordial gas and its physical state. Its temperature, its density, its very texture played a decisive role in how the story of reionization unfolded. It was far from a passive backdrop. It was an active participant, a reactive environment whose properties either aided or resisted the advancing wave of ionization. Before the first stars switched on, the intergalactic medium was cold and neutral. As the universe expanded from its hot, dense beginning, this primordial gas cooled dramatically, eventually settling into a frigid state, just a few tens of degrees above absolute zero. It was also incredibly smooth, a relic of the near uniformity of the Big Bang, though it was already beginning to be sculpted by the invisible hand of dark matter. The gas was slowly falling into the gravitational potential wells of the emerging cosmic web, creating a landscape of subtle density variations, dense knots at the intersections of filaments and vast, underdense voids in between. This initial coldness and relative smoothness were crucial. Cold, dense hydrogen gas is very effective at absorbing the specific ultraviolet light needed to ionize it. A brilliant early galaxy shining into this cold, dense fog would find its ionizing radiation quickly swallowed, its reach limited to a small bubble around itself. The reionization process would have been slow-going, like trying to melt a thick sheet of solid ice with a single blowtorch. The heat is applied locally, but the ice overall remains largely intact. The moment the first sources of light turned on, they began to fundamentally alter this environment. The initial effect was a dramatic and local heating. As the high-energy ultraviolet photons from stars and quasars streamed into the neutral gas, they didn't just ionize it, they transferred a tremendous amount of energy to the liberated electrons. This process, known as photoheating, caused the temperature of the intergalactic gas in the newly ionized regions to skyrocket, from a few dozen degrees to upwards of 10,000, 20,000, or even 30,000 degrees Celsius. This created a dramatic thermal pressure difference. The newly ionized, superheated gas inside an ionization bubble wanted to expand violently outward, while the cold, neutral gas outside resisted its advance. This set up a complex interplay, a cosmic battle between radiation pressure and gravitational infall. The expanding front of an ionization bubble could, in some cases, sweep up the surrounding neutral gas like a snowplow, compressing it into a dense, cold shell that actually became even more difficult for subsequent ionizing radiation to penetrate. In this way, the process of ionization could sometimes create its own temporary barriers. This leads us directly to the concept of clumpiness, which is arguably the single most important property of the intergalactic medium during this era. The gas between galaxies was not a perfectly smooth fluid. It was a frothy, textured substance filled with density fluctuations. The dark matter cosmic web provided the underlying skeleton, and the gas traced this structure, forming a network of diffuse filaments connecting denser knots of matter. Within this web, there were random fluctuations. Some regions were slightly denser than others, and over time, gravity amplified these differences. Think of it like a sponge. If you try to clean a smooth surface with a damp cloth, the water spreads evenly. But if you try to clean a sponge, the water first soaks into the easiest, most porous pathways, while the dense, compact clumps remain dry for much longer. The reionization of the universe proceeded in much the same way. The ionizing radiation from the first galaxies preferentially flooded the low-density voids and channels first. These regions were easier to clear because there were simply fewer hydrogen atoms per cubic meter to ionize. The radiation could travel vast distances through these voids, creating large, connected bubbles of transparency. The dense clumps and filaments, however, were a different story. A dense cloud of neutral hydrogen presents a formidable obstacle. It acts as a cosmic roadblock, absorbing the incoming ionizing radiation and shielding the neutral gas that lies behind it. For reionization to complete, every last one of these dense clumps had to be individually evaporated or blasted apart. This made the final stages of reionization a protracted and inefficient mop-up operation. Clearing the first 90% of the neutral hydrogen might have been relatively swift as the radiation flooded the easy, low-density volumes, but eradicating the last stubborn 10%, hiding in the densest knots of the cosmic web, could have taken almost as long again. This inside-out model of reionization, where the underdense regions ionize first and the overdense regions last, is a key prediction that astronomers are now testing with observations. The clumpiness of the intergalactic medium meant that the universe did not become transparent all at once, but in a complex, patchy manner, with some regions remaining shrouded in neutral fog long after their neighbors had been brilliantly illuminated. The temperature of the intergalactic medium during and after reionization left a permanent fossil record that we can still measure today. By studying the absorption lines in the spectra of distant quasars, astronomers can not only detect the presence of intervening hydrogen gas but also measure its temperature. The pattern of these lines, known as the Lyman alpha forest, acts as a cosmic thermometer for the universe across billions of years. The data tells a clear story. Following reionization, the intergalactic medium was left in a hot, ionized state. However, it didn't stay that hot forever. The expansion of the universe continually cools the gas adiabatically, and there were no new widespread sources of heating to maintain the high temperatures. So, over the subsequent billions of years, the intergalactic medium has been steadily cooling down. By measuring the rate of this cooling from the Lyman alpha forest, we can actually work backwards to estimate how hot the gas was heated during the reionization era itself. These measurements provide a crucial, independent check on our theoretical models, helping us constrain the intensity and duration of the cosmic dawn. The state of the intergalactic medium, therefore, is not just a historical footnote. It is a dynamic character in the story, whose properties dictated the pace of the narrative and whose fossilized remains provide us with the evidence we need to piece that story together billions of years later. And so we arrive at one of the most elegant and powerful tools in the entire Cosmic Detectives kit, a phenomenon that allows us to read the history of the universe's gas written directly in the oldest light we can capture. This is the mystery of the Lyman alpha forest, a beautiful and complex spectral pattern that acts as a direct fossil record of the intergalactic medium throughout cosmic time. To understand it, picture the light from an incredibly distant quasar, a beacon shining from the epoch of reionization itself. As this brilliant beam of light travels across billions of light years towards our telescopes, it doesn't journey through a perfect vacuum. It passes through an immense, diffuse network of hydrogen gas clouds and filaments, the very backbone of the cosmic web. Whenever this starlight encounters a cloud of neutral hydrogen, the gas acts like a filter, absorbing a very specific, tiny amount of energy. The hydrogen atom is particularly fond of absorbing light at a precise ultraviolet wavelength known as the Lyman alpha line. Each time the quasar's light passes through a different cloud at a different distance, a different absorption line appears in its spectrum. The result is a stunning and intricate barcode of dark lines superimposed on the quasar's rainbow of colors, a forest of absorption features, all at slightly different wavelengths, with each line representing a separate cloud of hydrogen that the light encountered on its long journey to Earth. The true magic of the Lyman Alpha forest, however, lies not in its appearance, but in what it can tell us about the expansion of the universe itself. Because the cosmos is constantly stretching, the light from the quasar is stretched along with it, its wavelength systematically redshifted. But each intervening hydrogen cloud is also at a different distance, and therefore its own absorption line is redshifted by a different amount. This creates a direct mapping between the wavelength of an absorption line and the distance to the cloud that caused it. By analyzing the pattern of the forest, astrophysicists can effectively create a core sample of the universe's history, slicing through time and seeing how the distribution of neutral hydrogen changed from the present day all the way back to the reionization era. A rich, dense forest with many closely spaced lines tells us we are looking at an epoch when the universe was filled with many small, dense clouds of neutral gas. A sparse forest with fewer, broader lines indicates a later time when the gas was more uniformly ionized and diffuse. During the heart of the reionization era, this forest undergoes a dramatic and telling transformation. Before reionization began, when the universe was a thick, neutral fog, the Lyman Alpha forest would have been completely impassable. The light from any distant quasar would have been entirely absorbed before it could travel far, resulting in what astronomers call a Gunn-Peterson trough, a complete and stark absence of light in the Lyman Alpha part of the spectrum. It would be the spectral signature of a truly dark and opaque cosmos. As the first stars and galaxies began to ignite, they started to clear the fog, creating bubbles of ionized transparency. Within these bubbles, the quasar's light could travel freely, but as soon as it hit the edge of the bubble and entered the still neutral outer regions, it would be absorbed again. This creates a complex and evolving picture. As reionization progresses, the Gunn-Peterson trough becomes punctuated with isolated transmission spikes, narrow windows where the light managed to get through, corresponding to the ionized bubbles. Over hundreds of millions of years, these spikes multiply and merge, the trough gradually fills in, and the dense primordial forest thins out into the more open, modern woodland we see in the spectra of closer quasars. Interpreting this complex fossil record, however, is one of the most formidable challenges in modern astrophysics. The primary difficulty is untangling the effects of the gas distribution from the effects of the ionizing background. Is the forest sparse because there are simply fewer hydrogen clouds, or is it because a stronger ambient ultraviolet radiation field has ionized most of the gas, making the clouds disappear? It's like trying to determine if a landscape is dry because it hasn't rained, or because the sun is so intense that it evaporates all the water immediately. To solve this, scientists must combine the Lyman Alpha forest data with sophisticated computer simulations that model the growth of the cosmic web and the propagation of ionizing radiation. They run virtual universes with different reionization histories and then compare the simulated Lyman Alpha forests they produce with the real one observed by our telescopes. It is a painstaking process of matching a digital fossil to a real one, and it requires grappling with the inherent clumpiness of the early universe. A single, incredibly dense cloud of hydrogen can cast a shadow so deep it mimics the effect of a much larger region of neutral gas, potentially tricking us into thinking a certain part of the universe was still dark long after it had actually been cleared. Despite these challenges, the Lyman Alpha forest remains our most direct probe into the conditions of the early intergalactic medium. By studying its detailed structure, we can estimate the temperature of the gas left in the wake of reionization, measure the intensity of the primordial ultraviolet background radiation, and even hunt for the fingerprints of the very first stars and galaxies. Each absorption line is a whisper from a specific time and place in the cosmic past, and by listening to the entire chorus of the forest, we can begin to reconstruct the epic story of how our universe was flooded with light, one ionized bubble at a time. But as we chart the influence of those first brilliant quasars, we inevitably confront a mystery so profound it challenges our understanding of how cosmic structures can form at all: the origin of the supermassive black holes that powered them. The sheer scale of the problem is staggering. We have observed quasars fueled by black holes with masses exceeding 1 billion suns, shining brilliantly when the universe was less than 700 million years old. To put that in perspective, that's not enough time to grow such a monster through the conventional method of a star collapsing and then slowly, painstakingly accreting gas over eons. It's like finding a fully grown, towering redwood tree sprouting from a sapling that was planted only a few months ago. The existence of these cosmic giants so early in the universe's history presents a glaring timing problem, and solving it is absolutely critical, because the way these black holes formed directly influenced how and when they flooded the cosmos with the ionizing radiation that cleared the primordial fog. Scientists are actively investigating two primary, competing theories for their rapid formation, and each one paints a very different picture of the early cosmos. The first theory is the stellar seed model. In this scenario, the very first generation of stars, the population 3 stars we discussed earlier, were not just massive but truly colossal, some containing the mass of several hundred suns. When such a star reached the end of its brief, furious life, it wouldn't just go supernova. Its core could collapse directly into a black hole, creating a seed with an initial mass of perhaps a few hundred solar masses. This is a hefty starting point, much larger than the black holes formed from modern supernova. This seed would then sit at the center of a young galaxy, gorging on the abundant surrounding gas at a prodigious rate. Through a process known as Eddington limited accretion, there's a maximum speed at which a black hole can consistently pull in matter, governed by the pressure of its own radiation pushing back. Even at this maximum theoretical rate, growing a several hundred solar mass seed into a billion solar mass behemoth in less than 700 million years is an immense challenge. It would require the seed to form extremely early and to feed in an almost uninterrupted perfect frenzy, a scenario that pushes the limits of our physical models. The second, more exotic theory is the direct collapse model. This bypasses the need for stars entirely. Imagine one of those dense knots of dark matter at the intersection of the early cosmic web. Vast rivers of pristine hydrogen and helium gas, still devoid of heavy elements, flow into this central region. Normally, this gas would need to cool and fragment to form stars. But in this specific scenario, a powerful external source of ultraviolet radiation, perhaps from a nearby, vigorously star-forming galaxy, bathes the gas cloud. This intense radiation prevents the hydrogen atoms from pairing up to form molecules. Since molecular hydrogen is a very efficient coolant, without it, the gas cannot lose its heat and fragment into stars. Instead, the entire gigantic cloud, containing the mass of tens or even hundreds of thousands of suns, remains hot and begins to collapse monolithically, catastrophically, under its own immense gravity. It spirals inward in a violent, chaotic storm of gas, eventually becoming so dense that it bypasses the star formation stage completely and collapses directly into a single, massive black hole seed. This seed could be born with a stupendous initial mass of 10,000 to 100,000 suns, a colossal head start in the growth race. The implications of which model is correct are huge for the story of reionization. A universe where supermassive black holes grow from direct collapse seeds would have a very different ionization history than one where they grow from stellar remnants. A direct collapse black hole is born big and can immediately begin accreting gas and shining as a bright mini-quasar. This means powerful sources of ionizing radiation could switch on very early, perhaps even before the host galaxy has had time to form a significant population of stars. They could be the pioneers, creating the very first large ionized bubbles in the neutral fog and potentially triggering further star formation in the surrounding gas through their intense radiation pressure. In contrast, a stellar seed black hole would take longer to reach a dominant size. Its early influence would be more localized, and the galaxy's starlight might be the primary ionizing source for a longer period before the black hole grew powerful enough to contribute significantly. The origin mechanism of these black holes, therefore, isn't just a question of their own birth. It sets the clock for when one of the most potent ionizing engines in the universe could begin its work, shaping the timeline and the very geometry of the reionization process from its earliest moments. And so we have followed the epic story of how hydrogen, the universe's primary element, was torn from its neutral state and flooded with light. But hydrogen did not journey alone. It had a silent partner, a constituent that makes up nearly a quarter of the ordinary matter in the cosmos, helium. And the story of helium's own reionization forms a fascinating second-act mystery that unfolded long after the cosmic fog of hydrogen had cleared, revealing a later, more violent chapter in the universe's history. While hydrogen reionization was a drama driven by the collective power of starlight, the reionization of helium required something far more potent, pointing a finger directly at the most energetic engines in existence. To understand why, we need to look at the atomic structure of helium itself. A neutral helium atom has 2 electrons, and they are bound to the nucleus with significantly more force than the single electron in a hydrogen atom. Ripping that first electron away requires an ultraviolet photon with an energy of 24.6 electron volts. That's already more energetic than the photons responsible for hydrogen reionization. But to fully ionize helium, to strip away its second, even more tightly bound electron, you need a truly fierce particle of light, an extreme ultraviolet photon with a whopping 54.4 electron volts of energy. Think of it as the difference between prying open a simple wooden box and cracking a high-security vault. The hot, young stars that were so effective at ionizing hydrogen simply don't produce enough of this high-energy radiation. Their surface temperatures aren't scorching enough to flood space with the required torrent of extreme ultraviolet photons. For helium, a more specialized and far more violent tool was needed: the brilliant, matter-devouring fury of quasars. This creates a distinct 2-part narrative for the universe's clearing. The first act, the epoch of hydrogen reionization, was likely completed by the time the universe was around 1 billion years old, a communal effort led by countless early galaxies. This left the cosmos transparent to most optical and ultraviolet light, but the helium atoms, while often singly ionized, largely retained their second electron. The intergalactic medium was now a sea of transparent plasma, but it was a plasma still seeded with these stubborn, doubly neutral helium atoms. Then the second act began. As the universe aged to perhaps 2 or 3 billion years old, galaxies had grown larger and had merged, and at their centers, their supermassive black holes had grown to truly colossal proportions. These monsters began to shine forth as the most luminous quasars, and their accretion disks, searing with heat, became prodigious factories for the X-rays and extreme ultraviolet radiation needed to blast apart the last fortress of the helium atom. Pinpointing exactly when this helium reionization occurred is a major challenge for cosmologists. Unlike the hydrogen reionization, which left a clear signature in the cosmic microwave background and created the Gunn-Peterson trough for distant quasars, the evidence for helium reionization is more subtle. Our primary clue comes once again from the Lyman alpha forest, but this time we look for the specific absorption signature of singly ionized helium, known as helium-2. Just as neutral hydrogen absorbs light at a specific wavelength, singly ionized helium has its own unique absorption line in the far ultraviolet. When astronomers analyze the spectra of quasars at different distances, and therefore from different cosmic eras, they can search for a telltale trough in the helium, the second absorption. What they find is fascinating. For quasars from when the universe was older than about 3 billion years, there is little to no absorption, indicating that the helium was fully ionized. But when we look at the light from quasars from when the universe was younger, around 2 billion years old or less, a pronounced helium, the second trough, appears. This suggests that between a redshift of 3 and 2, or roughly between 2 and 3 billion years after the Big Bang, a final, pervasive wave of ionization swept through the cosmos, targeting and finishing off the remaining neutral helium. This was not a gentle process. The energy required to doubly ionize helium is immense, and when that energy was dumped into the intergalactic medium, it had dramatic consequences. This event essentially reheated the universe. Following hydrogen reionization, the cosmos had been steadily cooling due to its relentless expansion. But helium reionization, driven by the intense quasar radiation, injected a tremendous amount of heat back into the gas that fills the space between galaxies. This wasn't a uniform warming, it was a patchy, burst-like heating that tracked the distribution of the quasars themselves. Regions of space near a brilliant quasar would be heated to temperatures of 30 to 40,000 degrees Celsius or more, while more remote voids might have remained relatively cool. This created a new level of complexity in the intergalactic medium, raising its thermal pressure and potentially affecting the flow of gas into and out of galaxies, which in turn could have influenced the rates at which new stars were born. The delayed and violent nature of helium reionization adds a final, crucial layer to our understanding of the universe's journey to transparency. It shows us that the clearing of the cosmos was not a single, monolithic event, but a multi-stage process orchestrated by different cosmic actors at different times. First, the collective starlight of nascent galaxies cleared the hydrogen fog, ending the true cosmic dark ages. Then, billions of years later, the concentrated fury of quasars finished the job, blasting apart the last stubborn atomic holdouts and heating the intergalactic medium to a new peak. This two-part story underscores a profound truth. The history of our universe is written not just in the birth of light, but in its evolving character as the baton of cosmic transformation passed from the countless faint sparks of the first galaxies to the brilliant, isolated beacons of the most powerful black holes. But for all the grandeur of this cosmic story, the evidence we seek is written in the faintest of whispers, in light that has traveled for over 13 billion years and is now incredibly fragile and elusive. Observing the reionization era directly is one of the most formidable technical challenges humanity has ever undertaken, a task that pushes the very limits of engineering and physics. The primary obstacle is a simple but profound effect of the expanding universe, cosmological redshift. The light emitted by the first stars and galaxies was originally brilliant, hot, and ultraviolet. But as it has journeyed across the expanding cosmos for billions of years, the very fabric of space has stretched, and in doing so, it has stretched the wavelength of that ancient light. That once short, high-energy ultraviolet radiation has been stretched or redshifted all the way into the infrared part of the electromagnetic spectrum. It's as if the universe has taken a brilliant symphony and played it back at an incredibly low pitch, shifting it into a register that is completely invisible to our eyes and to traditional optical telescopes like Hubble. To see this light, we need an eye that can see in the dark, a telescope specifically designed to detect this faint, ancient infrared glow. This is the revolutionary purpose of the James Webb Space Telescope. Its entire design is a masterpiece of cosmic engineering tailored to this single problem. Its massive, gold-coated mirror is built to be enormous, gathering every possible precious photon of this faint infrared light. Its instruments are cooled to incredibly low temperatures, just a few tens of degrees above absolute zero, to eliminate its own infrared glow, which would otherwise completely drown out the subtle signal from the early universe. And its location, a million miles from Earth at the Lagrange 2 point, keeps it in the deep freeze of shadow, away from the heat and light of our planet and moon. Webb is not just an improvement over previous telescopes, it is a quantum leap, a completely new kind of observatory that acts as a time machine, allowing us to directly photograph infant galaxies as they were just a few 100 million years after the Big Bang. Every deep field image it produces is more than a pretty picture. It is a core sample of cosmic history, providing the first solid census of the objects that were likely responsible for lighting up the cosmos. By counting these galaxies, measuring their brightness, and analyzing their infrared spectra, Webb is turning the theoretical narrative of reionization into a data-driven science, confirming some of our ideas while spectacularly shattering others. Yet, even Webb has its limitations. It is observing the sources of reionization, the stars and galaxies, but it cannot directly see the process itself. It shows us the lights being switched on, but it cannot map the shadows of the receding neutral fog between them. To witness that, we need to change our perspective entirely and listen instead of look. This is the promise of one of the most ambitious scientific projects ever conceived, the detection of the 21-centimeter signal from neutral hydrogen. As we discussed, every atom of neutral hydrogen in the early universe was faintly humming at this specific radio wavelength. By building radio telescopes sensitive enough to detect this signal after it has been redshifted to meter-long wavelengths, we could, in theory, create a three-dimensional map of the neutral hydrogen gas throughout cosmic time. This wouldn't just be a snapshot, it would be a dynamic movie of the reionization era. We could watch in real time across billions of years as the first brilliant bubbles of ionized plasma ignited, grew, and slowly merged, finally clearing the entire cosmic fog. It would be the ultimate documentary of the cosmic dawn. The challenge, however, is that this signal is almost unbelievably faint. It is millions of times weaker than the background radio noise from our own galaxy, from countless other astrophysical sources, and most problematically from our own civilization. FM radio stations, television broadcasts, satellite transmissions, and even everyday electronic devices create a cacophony of radio interference that utterly drowns out this primordial whisper. Detecting the cosmic 21-centimeter signal is like trying to hear a single pin drop in the middle of a roaring heavy metal concert. To overcome this, astronomers are building their telescopes in the most radio-quiet locations on Earth, the remote deserts of South Africa and the vast, empty outback of Western Australia. These sites are chosen because they are naturally shielded from human radio pollution, offering a window of radio silence through which we can try to listen to the ancient universe. The future of this endeavor rests on the Square Kilometre Array, or SCAR, a project that is the very definition of audacious. When completed, it will not be a single dish but a vast network of thousands of simple radio antennae spread across hundreds of kilometers in both South Africa and Australia. Together, they will form a collective collecting area of over 1 square kilometer, hence the name. This immense scale is necessary to achieve the sensitivity required to isolate the 21-centimeter signal from the cosmic static. The data processing requirements are almost beyond comprehension. The SKA will generate more data in a single day than the entire global internet traffic, requiring supercomputers that don't even exist yet to analyze it. This is not just astronomy, it is a grand technological and computational frontier. The goal is not to take a pretty picture, but to perform the most sensitive auditory archaeology imaginable, to hear the echoes of the universe's first great transformation and finally watch the cosmic dawn break, not as a series of still images, but as a glorious, unfolding film. Yet, to truly understand the timing of this great transformation, we must look to the oldest photograph in existence, a snapshot of the infant universe that holds within it the ghostly imprint of reionization itself. This brings us to the cosmic microwave background radiation, the cold, faint afterglow of the Big Bang that permeates all of space. For decades, we have studied its temperature fluctuations, the tiny hot and cold spots that are the blueprints for all future cosmic structure. But there is another, more subtle layer of information encoded in this ancient light, its polarization. This is the key that unlocks our 15th mystery, offering a completely independent way to peer into the reionization era. Polarization is a property of light that describes the orientation of its vibrating electric field. Most light we encounter is unpolarized, meaning its waves vibrate in all possible directions perpendicular to its travel. But when light scatters off of particles like dust or free electrons, it can become polarized, its waves preferring to vibrate in a particular direction. Think of sunlight glinting off the surface of a lake. The light that reflects directly toward you becomes polarized horizontally, which is why polarized sunglasses with their vertical filters can effectively block that blinding glare. A similar, though far more subtle, scattering event happened on a cosmic scale during the reionization era, and it left a permanent mark on the cosmic microwave background. The story of this polarization has two distinct chapters. The first and primary polarization occurred when the universe was just 380,000 years old at the moment of recombination. This was when the hot, dense plasma of the early universe cooled enough for electrons and protons to combine and form neutral hydrogen atoms, suddenly making the cosmos transparent and releasing the CMB light we see today. In that final instant before the photons began their free journey across the universe, they scattered off the last of the free electrons. This scattering imprinted a specific, swirling pattern of polarization on the CMB, often called an E-mode pattern. This pattern is fundamentally linked to the density fluctuations of the early universe, the seeds of future galaxies. But then, hundreds of millions of years later, the second chapter unfolded. As the first stars and quasars turned on, they began reionizing the hydrogen, ripping electrons away from their atoms and flooding the universe with a new population of free electrons. When the ancient CMB photons, still traveling across the cosmos, encountered these newly freed electrons during the reionization era, they scattered one more time. This secondary scattering did not create a new pattern from scratch. Instead, it partially reprocessed the existing light, adding a new layer of polarization on top of the primordial one. It's like a master painter adding a final, subtle glaze over a finished canvas, subtly altering the overall appearance and texture of the work. The specific type of polarization generated by this rescattering is crucial. The reionization process was a large-scale event, and the scattering off the newly freed electrons occurred over immense distances. This large angular scale scattering produced a distinct signature in the CMB polarization, particularly enhancing what is known as the E-mode power on the very largest scales we can observe. More importantly, it also generated a much fainter, more elusive component called B-mode polarization. While E-modes are curling patterns that can be thought of as having no handedness, B-modes are a twisting, curl-like pattern that can potentially hold the key to even grander mysteries, like the inflationary expansion of the universe in its first fraction of a second. The reionization-induced B-modes are a specific type, a signal created not by primordial gravitational waves but by the lensing effect of the rescattering itself. By carefully measuring the amplitude of the polarization on these largest angular scales, cosmologists can effectively work backwards to estimate the total number of scattering events that occurred during reionization. Since the number of scatterings depends directly on the total number of free electrons, and that number is determined by how much of the universe was ionized and for how long, this measurement gives us a powerful, integral constraint on the entire reionization history. This is precisely what ambitious space missions like the Planck satellite have done. By meticulously mapping the all-sky polarization of the cosmic microwave background with incredible sensitivity, Planck was able to measure this large-scale polarization signal and derive a key number, the optical depth to reionization, often denoted by the Greek letter tau. This single number represents the probability that a CMB photon scattered off a free electron after recombination. The value measured by Planck, approximately 0.055, tells us that reionization was a relatively late event in cosmic history. When translated into a timeline, it suggests that the universe was about half ionized by the time it was around 450 million years old, and the process was largely complete by the 1 billion year mark. This provides a critical anchor point, a global average that all our other observations must eventually match. However, this elegant picture is not without its own puzzles. The mystery lies in the fact that this single number, the optical depth, leaves room for interpretation about the precise details of how reionization unfolded. The polarization signal gives us a robust measure of the total integrated effect of reionization, but it does not, on its own, tell us the detailed shape of the story. It tells us the total amount of water that flowed through a river over a year, but it doesn't tell us if that flow was a steady trickle, a series of seasonal floods, or one massive deluge. For instance, a model where reionization started very early and progressed slowly and gradually could produce a similar optical depth to a model where it started later but proceeded in a much more rapid, explosive fashion. The Planck data, while incredibly precise, cannot yet definitively distinguish between these different narrative arcs. This is why we need to combine the CMB polarization data with all our other lines of evidence, the observations of distant quasars, the census of early galaxies from James Webb, and the future maps from the 21-centimeter experiments. The CMB polarization provides the crucial, overarching constraint, the final word on the total budget of ionizing photons that must have been produced. It tells us the universe's final answer, but it is up to our other telescopes to uncover the detailed working out of the problem, revealing whether the cosmic dawn was a patient, prolonged sunrise or a dramatic, abrupt flash of light that forever changed the nature of the cosmos. As we chart the influence of massive stars and brilliant quasars, we must now confront an invisible and almost ghostly force that may have subtly guided the entire drama of cosmic dawn: primordial magnetic fields. We are accustomed to thinking of the cosmos in terms of gravity and radiation, but magnetism represents a third, deeply mysterious player. Today, we observe magnetic fields woven throughout the fabric of space, threading through galaxies, directing the flow of cosmic rays, and shaping the birth of stars. But where did these fields come from? Did they emerge with the Big Bang itself, or were they forged later in the furnaces of the first stars? Their potential role during the reionization era is one of the most speculative and fascinating frontiers in cosmology, a hidden dimension that could have influenced everything from the formation of the very first stars to the large-scale structure of the ionized bubbles that cleared the cosmic fog. The central question is one of origins. Did the infant universe possess weak, all-pervading, seed magnetic fields? One compelling theory suggests they were generated in the incredibly violent processes of the very early universe, perhaps during a phase of rapid expansion known as inflation, or in the turbulent aftermath of the Big Bang. These primordial fields would have been unimaginably weak, billions of times fainter than the magnetic field of the Earth, and spread uniformly throughout the cosmos. Another possibility is that they were born locally, created by the first astrophysical objects themselves. The turbulent dynamos inside the first proto-galaxies, or the shock waves from the earliest supernova explosions, could have amplified tiny fluctuations into organized magnetic fields that were then blasted out into intergalactic space. The challenge for scientists is that these initial seed fields, regardless of their origin, would have left almost no direct observable trace on the cosmic microwave background, forcing us to look for more indirect clues to their existence and strength. If such fields did exist, even in a feeble state, their influence on the collapse of the first gas clouds could have been profound. The formation of a star is a battle between gravity, which pulls gas inward, and various forms of pressure that push back. Magnetic fields introduce a new form of pressure, magnetic pressure, and a phenomenon known as magnetic tension. Imagine a cloud of primordial hydrogen and helium gas beginning to condense under its own weight within a dark matter halo. Weak magnetic field lines would be frozen into this gas, and as the cloud contracts, these lines would be squeezed together and strengthened. This can provide crucial support against gravity, effectively propping up the cloud and slowing its collapse. This delayed collapse might have had a significant impact on the initial mass function of the very first stars. Without magnetic fields, gas could collapse monolithically into those monstrous population 3 stars. But with magnetic fields providing extra support, the gas might have fragmented differently, potentially leading to a broader range of stellar masses from the very beginning, including more smaller, longer-lived stars. This would mean that the first stellar populations were more diverse than we thought, which in turn would affect the total amount and duration of ionizing radiation they produced. Beyond the birth of stars, these cosmic magnetic fields could have acted as invisible channels and barriers for the radiation that drove reionization. Ionizing ultraviolet photons travel in straight lines, but they are affected by the medium through which they pass. A magnetized intergalactic medium is not a perfectly smooth fluid. The field lines can create a kind of cosmic grain, a directional structure. Ionized plasma, being made of charged particles, is forced to move along these magnetic field lines, much like beads on a wire. This means that the bubbles of ionized plasma created by the first galaxies and quasars might not have been perfect spheres. Instead, they could have grown preferentially along the directions of the local magnetic field, forming elongated, filament-like structures that reached out into the neutral fog. This magnetic guidance could have accelerated the merging of ionized bubbles from different sources, helping the reionization process to connect vast regions of space more quickly than it could have in a purely neutral, non-magnetized environment. Conversely, magnetic fields could also have protected some dense, neutral clumps. The fields might have provided extra confinement, holding the gas together against the evaporating effect of the ionizing radiation, making certain pockets of the cosmic fog more resilient and longer-lasting. The feedback from the first supernova, which we know was crucial for clearing pathways for light and enriching the cosmos with heavy elements, would also have been dramatically different in a magnetized universe. A supernova explosion is not a symmetric event. It drives powerful jets and outflows. Magnetic fields can collimate these outflows, focusing them into narrow, high-energy jets that can punch through the galactic gas much more efficiently than a spherical blast wave. This means that in a galaxy with even a weak magnetic field, supernova could have carved out longer, clearer tunnels through the interstellar medium, drastically increasing the escape fraction of ionizing photons from subsequent generations of stars. The magnetic fields would have acted as cosmic focusing lenses, directing the explosive energy to where it could do the most work in clearing a path for light. Furthermore, when these magnetically driven winds expanded out into the intergalactic medium, they would have carried these magnetic fields with them, effectively seeding the vast voids with this invisible force. This process, known as galactic feedback, could have been the primary mechanism for building the large-scale cosmic magnetic fields we observe today, spreading them from their original stellar nurseries out to fill the entire cosmos. The hunt for evidence of these primordial magnetic fields is now underway, using some of the most subtle techniques in astronomy. One promising method involves studying the cosmic microwave background with even greater precision. While the primary CMB temperature fluctuations are largely unaffected by weak magnetic fields, the polarization of this ancient light could hold a faint signature. Primordial magnetic fields would have generated extra turbulence and vector modes in the plasma of the early universe, potentially leaving a unique, twisted imprint on the CMB's mode polarization patterns. Distinguishing this signal from the one created by inflationary gravitational waves is a monumental task, but it is theoretically possible. Another approach is to look at the effect of magnetic fields on the distribution of matter itself. Magnetic pressure suppresses the formation of the very smallest structures in the universe. By using telescopes like James Webb to conduct an ultra-deep census of the faintest dwarf galaxies in the early universe, astronomers might find a clue. If there is a surprising scarcity of these tiny galaxies compared to cosmological predictions, it could be indirect evidence that primordial magnetic fields were providing extra support, preventing the smallest clumps of gas from ever collapsing into stars. Ultimately, the mystery of cosmic magnetic fields reminds us that the story of reionization is not yet fully written. We have focused so intently on the brilliant actors, the stars, the galaxies, the quasars, that we may have overlooked the subtle stagehands shaping the play from the shadows. These invisible fields could have been the great organizers of the cosmic dawn, gently guiding the flow of gas, focusing the explosions of dying stars, and channeling the light that ultimately burned away the primordial fog. Their potential influence ties the vast scale of the universe's expansion to the intimate details of star formation, linking the physics of the very first instant to the creation of the transparent cosmos we call home. Unraveling this mystery will require a new generation of telescopes and a deeper understanding of plasma physics, pushing us to listen not just for the light of the first stars, but for the silent magnetic symphony that may have accompanied them. After exploring the profound influence of invisible magnetic fields, we arrive at a mystery that strikes at the very heart of our confidence in the reionization story. A potential cosmic accounting error so significant it has been termed the photon underproduction crisis. Imagine meticulously calculating the budget needed to build a city, only to discover the final, magnificent metropolis standing before you, seemingly constructed for half the cost. This is the essence of the crisis. Our most sophisticated computer simulations, which model the formation of early galaxies and their production of ionizing ultraviolet photons, are consistently coming up short. When they tally the total number of photons that known populations of stars and quasars should have produced, the sum falls significantly below the colossal energy requirement we know was necessary to ionize the entire universe by the 1 billion-year mark. It appears we are missing a tremendous amount of cosmic currency, and the ledger of the early universe does not balance. One of the most straightforward and compelling resolutions to this crisis points directly back to the populations of galaxies we've already discussed. Our current galaxy censuses, even from the powerful James Webb Space Telescope, are almost certainly incomplete. We are likely only seeing the very brightest, most massive galactic cities from that era. But what about the countless dim, small-town equivalents? There could exist an immense hidden populace of ultra-faint dwarf galaxies, so dim that their collective light slips below our current detection threshold. Think of trying to count every light in a vast, sprawling metropolis from an airplane at night. You can easily spot the bright downtown centers and major highways, but you would completely miss the glow from millions of individual household porch lights, street lamps in quiet neighborhoods, and small shops. Yet, if you added up all that mist diffuse illumination, it could rival or even exceed the light from the brilliant downtown core. In the cosmic context, if these faint, undiscovered galaxies were numerous enough, their combined ionizing output could easily fill the photon budget gap. They represent the missing middle class of the cosmic economy, the unseen workforce whose collective labor could have powered the Great Clearing. Another potential fix lies not in the number of photon factories, but in their efficiency. This brings us back to the critical concept of the escape fraction. Our simulations have to make assumptions about how much of the ionizing radiation generated inside a galaxy actually escapes into intergalactic space. Historically, models have often assumed a relatively low conservative value, perhaps only 5 or 10%, to account for the fact that gas and dust within a galaxy are excellent at trapping this high-energy light. But what if the early universe was far leakier than we ever imagined? What if the escape fraction wasn't a modest 5%, but a torrential 30, 40, or even 50%? The pristine, low metallicity gas in the earliest galaxies, constantly churned and blown clear by violent supernova explosions, could have been incredibly porous. In this scenario, we wouldn't need more galaxies. We just need the galaxies we already know about to be far more effective at broadcasting their light into the cosmos. A small adjustment to this single variable in our models could resolve the entire deficit, turning a crisis into a testament to the raw, unbridled power and efficiency of the universe's first stellar nurseries. Yet, if hidden galaxies and higher escape fractions aren't sufficient to solve the problem, we may be forced to consider more exotic and revolutionary possibilities. Perhaps our understanding of the stars themselves is incomplete. The first generation of stars, the population 3 behemoths, were fantastically efficient producers of ionizing photons. If they were even more common or lived in a slightly different way than our current stellar physics predicts, they could have provided a tremendous early burst of ionizing radiation that our models are underestimating. Alternatively, could there have been other, more mysterious contributors to the cosmic energy budget? Some theorists have even explored the possibility of annihilating or decaying dark matter particles. While this sounds like science fiction, it's a serious line of inquiry. If certain types of dark matter particles could interact and annihilate each other, they would release a flood of energy, including high-energy photons that could contribute to reionization. This would be a truly fundamental shift, introducing an entirely new, non-stellar actor into the drama of cosmic dawn, one whose faint glow would be woven throughout the fabric of space itself, providing a pervasive background source of ionization that helped the stellar sources finish the job. Ultimately, the photon underproduction crisis is not a failure of science, but a thrilling indication that we are on the verge of a major discovery. It forces us to question our assumptions and to look deeper and more creatively at the data we are now collecting. The crisis acts as a powerful guide, telling observational astronomers exactly what to look for next, those elusive faint galaxies and clearer signatures of radiation escaping from early galactic disks. It also pushes theoretical astrophysicists to refine their models, to better simulate the chaotic, violent interiors of the first galaxies and to explore the wilder shores of particle physics. This apparent shortfall in photons is not a dead end. It is a signpost pointing toward a richer, more complex, and potentially more wondrous narrative of how our universe transformed itself from darkness to light. And so the cosmic dawn did not merely illuminate the universe. It also established its rules, setting in motion a chain of events that would dictate the fate of galaxies for billions of years to come. Having flooded the cosmos with a pervasive, energetic background of ultraviolet radiation, the reionization era did not simply end, it left behind a powerful and lasting legacy. This radiation became a permanent feature of intergalactic space, a kind of cosmic climate that every galaxy born afterward would have to contend with. It's a profound shift in perspective. The same light that freed the universe from its primordial fog also became a regulatory force, a universal feedback mechanism that profoundly suppressed the growth of the smallest galaxies and, in doing so, sculpted the entire galactic ecosystem we observe around us today. This is the great cosmic downsizing, a pivotal mystery that connects the violent birth of the first stars directly to the modern diversity of galaxies. To understand this, we need to picture a typical small, low-mass galaxy trying to form in the aftermath of reionization. Before this era, such a galaxy would have had a relatively straightforward path to growth. Its modest gravitational pull, provided by its dark matter halo, would slowly draw in cool, neutral hydrogen gas from its surroundings. This gas could then settle, condense, and eventually fragment to form new stars. But after reionization, the environment became far more hostile. The space between galaxies was now filled with this energetic ultraviolet background radiation, a sea of invisible photons constantly flooding every corner of the cosmos. For a massive galaxy like our own Milky Way with a deep gravitational well, this was a minor inconvenience, but for a fledgling dwarf galaxy with a much weaker gravitational hold on its gas, this radiation was an existential threat. The mechanism is both elegant and devastating. When a photon from this pervasive ultraviolet background strikes a neutral hydrogen atom that has just been pulled into a small galaxy, it doesn't just bounce off. It has enough energy to ionize the atom, ripping the electron away from the proton. This process doesn't just change the atom's state, it transfers a significant amount of kinetic energy to the newly freed electron, effectively heating the surrounding gas. Now, instead of a cloud of cold, calm gas ready to collapse and form stars, the galaxy finds itself trying to form stars from a hot, agitated plasma. The intense thermal pressure of this heated gas makes it incredibly difficult for it to compress down to the incredible densities required to ignite nuclear fusion. It's like trying to form a tightly packed snowball from a pile of hot, steamy slush. The material simply resists being compressed. In many cases, the gas becomes so hot that the galaxy's feeble gravity can no longer hold onto it at all. The heated gas can achieve escape velocity, streaming away from the dwarf galaxy in a process called photoevaporation, permanently stripping the galaxy of the raw material it needs to make future generations of stars. For countless small galaxies, the end of the cosmic dawn meant their own star-forming futures were effectively snuffed out, leaving them as dark, quiescent fossils. This process created a fundamental dividing line in the universe, a kind of cosmic mass threshold for survival. Galaxies residing in dark matter halos above a certain critical mass, roughly several billion times the mass of our Sun, had enough gravitational muscle to resist this pressure. They could continue to accrete gas, albeit with more difficulty, and sustain star formation. But any galaxy forming in a halo below this mass found itself in a desperate struggle. Its ability to form stars was severely hampered and in the smallest cases completely shut down. This had a dramatic effect on the predicted number of small galaxies. Computer simulations of cosmic structure formation that do not include this reionization feedback tend to predict a universe teeming with far more tiny, faint dwarf galaxies than we actually observe orbiting galaxies like our own. It is the inclusion of this heating effect that brings the models into alignment with reality, telling us that the reionizing background acted as a universal thermostat, effectively turning down the star formation in the smallest systems across the entire cosmos. This leads us directly to one of the most intriguing puzzles in modern galaxy formation, the missing satellites problem. Our most successful model of the universe, the lambda cold dark matter model, predicts that vast numbers of small dark matter clumps should be swarming around large galaxies like the Milky Way. If even a fraction of these clumps had managed to attract and cool gas to form stars, our night sky should be filled with hundreds of visible dwarf galaxy companions. Yet we only observe a few dozen. For a long time, this was a major point of tension between theory and observation. The key to resolving it appears to be the timing and intensity of reionization. The heating from the ultraviolet background didn't just make it hard for new small galaxies to form. It likely sterilized a huge population of them that had already begun to coalesce. Many of those predicted dark matter clumps are still there, invisible and dark, because the cosmic dawn robbed them of their gaseous fuel before they could ever truly shine. The reionization era, therefore, didn't just shape the galaxies we can see. It also determined the vast population of galaxies we cannot see, defining the shadows as well as the light. This universal suppression had another, more subtle consequence. It fundamentally altered the very chemistry of the universe's smallest galaxies. Consider the observable dwarf galaxies that did manage to survive, such as those orbiting the Milky Way. They display a fascinating and telling pattern. With very few exceptions, they all appear to have formed the overwhelming majority of their stars in a single, initial burst that occurred before the epoch of reionization was complete. After that, their star formation history is largely a flat line. It's as if they were caught in a flash freeze. They used up their initial reservoir of cool gas in that first frantic burst, and once the ultraviolet background switched on, they were never able to accrete and cool enough new gas to trigger a second act. This is why these dwarf galaxies are today so poor in metals, the elements heavier than hydrogen and helium. Subsequent generations of stars are the primary drivers of chemical enrichment, and without them, these galaxies were forever locked in a primitive state, cosmic time capsules from the universe's first chapters. Their stunted growth is a direct fossil record of the moment the universe became transparent, a permanent scar from the cosmic dawn. The impact of this cosmic downsizing reverberates all the way to the present day, influencing the properties of every galaxy we see. By effectively establishing a minimum mass for a star-forming galaxy, reionization created a much clearer distinction between different galactic populations. It helped create the dichotomy we observe between large, spiral galaxies with ongoing star formation and small, elliptical dwarf galaxies that are old, red, and dead. It amplified the differences dictated by the underlying dark matter distribution, ensuring that only the most massive nodes of the cosmic web could evolve into the brilliant galactic cities we see today. This feedback loop is a stunning example of how the universe regulates its own growth. The first stars and galaxies, through the very act of lighting up the cosmos, created an environment that prevented the majority of their potential smaller siblings from ever achieving the same brilliance. It was a self-limiting process where the pioneers, in their explosive birth, consciously or not, limited the competition for future resources. This grand-scale feedback shaped the hierarchy of the cosmos, favoring the growth of giants while keeping the vast population of dwarfs in check. And in doing so, it crafted the specific distribution of galaxies that allows us to tell this story billions of years later. Of course, the images from the James Webb Space Telescope are breathtaking, those brilliant, ruby-red smudges of ancient light that represent the universe's first galactic building blocks. But for the scientists trying to solve the mystery of reionization, a pretty picture, as stunning as it is only the beginning of the story. It's like identifying a suspect in a lineup. It tells you who was present at the scene, but it doesn't reveal what they did or how they did it. To get that crucial evidence, we need to move from a simple photograph to a forensic analysis, and that requires a completely different, more powerful technique, spectroscopy. This is the process of taking the collected light from one of these distant objects and passing it through a cosmic prism, splitting it into its constituent colors to create a detailed barcode of its energy signature. Within this barcode, these spectral lines, lie the definitive fingerprints of the physical processes at work inside the galaxy, its chemical composition, the temperature of its stars, its motion, and most importantly for our story, the telltale signs of its interaction with the neutral hydrogen fog that once filled the cosmos. The single most important spectral feature in this entire detective story is the Lyman alpha line. This is a very specific and powerful emission line produced by hydrogen atoms when their electrons make a particular energy jump. In a modern, unobstructed universe, we expect to see a bright, prominent Lyman alpha spike in the spectrum of any galaxy that is actively forming hot, young stars. These stars flood their galaxy with ultraviolet light, which energizes the surrounding hydrogen gas, causing it to glow brightly at this specific wavelength. It should be one of the most obvious and brilliant features in the spectrum of an early galaxy. But during the reionization era, this signal undergoes a dramatic transformation, and it's this transformation that holds the key. When a galaxy is embedded in a thick, neutral hydrogen fog, that fog doesn't just sit there passively. It acts as a brilliant cosmic thief. As the Lyman alpha light tries to escape the galaxy and travel across the universe toward us, it is immediately absorbed by the vast sea of neutral hydrogen atoms along the line of sight. These atoms are perfectly tuned to absorb this specific wavelength. The result is not just a dimming of the line, but in many cases a complete and total suppression. The brilliant Lyman alpha spike is abruptly chopped off, creating what astronomers call a Gunn-Peterson trough, a stark, silent gap in the spectrum where a vibrant signal should be. This profound absorption is our most direct weapon for mapping the progress of reionization. As the first galaxies and quasars ignite, they begin to clear the fog around them, creating growing bubbles of ionized, transparent space. Inside these bubbles, the hydrogen has been ripped apart into protons and electrons, and this plasma cannot absorb the Lyman alpha light. So, if a galaxy is sitting inside a large enough ionized bubble, its Lyman alpha emission can travel freely through the bubble until it reaches the bubble's edge. There, at the boundary where the ionized plasma meets the remaining neutral fog, the light is finally absorbed. This creates a powerful cosmic test. When we point a powerful spectrograph like the one on the James Webb Space Telescope at a galaxy from the reionization era, we are essentially conducting a simple yes or no experiment. Does its spectrum show a strong Lyman alpha emission line? If the answer is yes, then that galaxy is likely sitting in a large, already cleared region of the universe. It is a citizen of a transparent cosmic metropolis. If the answer is no, and the line is suppressed or completely absent, then that galaxy is still deeply shrouded in the neutral fog, its light struggling to escape from an isolated outpost in the dark ages. By performing this test on hundreds of galaxies at different distances, and therefore from different moments in cosmic time, we can begin to chart the growth of these transparent bubbles. We can watch statistically as the fraction of galaxies showing a Lyman alpha line increases over time, creating a direct observational movie of the reionization process itself. However, securing these spectra is one of the most arduous and technically demanding challenges in all of modern observational astronomy. The light from these early galaxies is not just incredibly faint, it is also dramatically stretched by the expansion of the universe. The Lyman alpha line, which is emitted in the ultraviolet, gets redshifted deep into the infrared part of the spectrum by the time it reaches us. This is why the James Webb Space Telescope, with its revolutionary infrared capabilities, is so essential. But even for Webb, this is a monumental task. Taking a spectrum requires collecting vastly more light than taking a simple image. The telescope must stare at a single, faint galaxy for hours, sometimes even dozens of hours, to gather enough precious photons to build up a spectrum with sufficient clarity to identify the crucial Lyman alpha feature. It is a painstaking, time-consuming process, and telescope time is the most precious commodity in all of astronomy. Every hour spent on one galaxy is an hour not spent on another, forcing teams to make difficult choices about which cosmic suspects to interrogate first. The challenge doesn't end with mere faintness. The intergalactic medium is not a smooth, uniform fog. It is a complex, clumpy web. This clumpiness means that the absorption of Lyman alpha light is not a simple all-or-nothing effect. It can be patchy and unpredictable. A galaxy might be partially visible through a fortunate, clear tunnel in the cosmic web, while another galaxy at the same distance might be completely obscured by a chance dense cloud of neutral hydrogen directly in our line of sight. This cosmic variance introduces a great deal of noise and uncertainty into our measurements. We can't just look at one or two galaxies and declare a whole era ionized or neutral. We need a large statistical sample scores, even hundreds of galaxy spectra from the same cosmic epoch, to average out these random fluctuations and get a true sense of the global conditions. Building this large sample is the primary spectroscopic goal of the Webb telescope's deep field observations, but it is a slow and meticulous undertaking, a cosmic census conducted one faint rainbow barcode at a time. Beyond the simple presence or absence of the Lyman alpha line, the detailed shape of the line itself holds a treasure trove of information. In galaxies where the line is present but has been slightly sculpted by residual neutral gas, its profile, whether it is symmetrical, skewed to one side, or has a truncated blue edge, can tell us about the velocity and distribution of the gas flowing into or out of the galaxy. This can reveal the powerful galactic winds driven by supernova, the very same winds that might be blowing holes in the interstellar medium and allowing ionizing photons to escape. Furthermore, spectroscopy doesn't just look at hydrogen. It can detect the faint signatures of other elements like oxygen and carbon, even in these incredibly early systems. Finding these heavier elements confirms that the galaxy is already being polluted by the ashes of previous supernova explosions, placing it in a later generation of stars after the first pristine population. 3 stars have already lived and died. This allows us to build a much more complete picture of the galaxy's life cycle, its age, its star formation history, and its chemical maturity, all from the subtle patterns hidden within its stretched and ancient light. The ongoing search for spectroscopic confirmation is therefore the crucial bridge between theory and observation in the story of reionization. The stunning images from Webb provide the cast of characters, but the spectra provide the script, the dialogue, and the stage directions. They tell us not just who was there, but what role they played in the cosmic drama. Each successfully captured spectrum from a galaxy at the edge of time is a hard-won piece of evidence, a direct measurement that either supports our grand theoretical models or, as has happened so often in this field, forces us to tear them up and start anew. As this spectroscopic census gradually expands, it will allow us to move from broad, speculative brushstrokes to a precise, data-driven timeline, finally revealing the exact sequence of events that transformed our universe from an opaque sea of darkness into the brilliant, transparent expanse we call home. This entire epic, the transformation of the cosmos from darkness to light, was not a simple, uniform event like a single light switch being flipped for the entire universe. Instead, it was a messy, chaotic, and deeply uneven process, a cosmic dawn that broke at different times in different places. This fundamental patchiness, the inhomogeneity of reionization, is our 20th mystery, and grappling with it is essential if we are to move from a simple cartoon of the event to a realistic, three-dimensional movie. The universe did not become transparent all at once. It was a gradual, bubbling percolation where islands of light slowly grew and merged until they filled the entire cosmic sea. To visualize this, don't think of a room where the lights slowly brighten everywhere simultaneously. Instead, picture a vast, foggy landscape on a cold morning. At first, the fog is total and impenetrable. Then, here and there, people light campfires. Each fire creates a small, spherical clearing in the fog around it, a pocket of warmth and visibility. For a long time, these clearings are isolated from one another, separated by walls of dense, persistent fog. But as more fires are lit, and as the existing fires grow larger, their individual clearings begin to expand. Eventually, the edges of 2 neighboring clearings touch and merge, forming a single, larger, irregularly shaped zone of clarity. This process continues, with bubbles merging into ever larger complexes, until the last stubborn patches of fog are finally burned away and the entire landscape is clear. This is the bubble model of reionization, and it fundamentally changes our understanding of the era. The universe was a cosmic Swiss cheese, with the ionized bubbles representing the holes and the neutral hydrogen acting as the cheese itself. The real mystery lies in the precise size, distribution, and growth of these bubbles. What determined their birth and their ultimate fate? the answer points directly to the underlying architecture of the cosmos. The first and most powerful sources of ionizing radiation, the brilliant quasars and the most massive star-forming galaxies, didn't form randomly. They were born in the densest nodes of the cosmic web, the places where the dark matter filaments intersected and where vast flows of primordial gas were funneled by gravity. It was in these cosmic metropolises that the first and largest ionized bubbles were ignited. A single, brilliant quasar with its intense, piercing radiation could blast out a truly colossal spherical cavity, perhaps millions of light years across, in the surrounding neutral fog. Similarly, a cluster of bright, early galaxies, all contributing their ultraviolet output, could create a huge, combined ionized region, a veritable super bubble of transparency. So, from the very beginning, the topology of reionization was imprinted with the pattern of the cosmic web itself. The bubbles were not scattered randomly. They traced the large-scale structure of the universe, lighting up first along the dense filaments and hubs where matter was concentrated. The growth of these bubbles was a complex battle between the relentless output of radiation and the stubborn resistance of the neutral gas. Initially, a bubble expands rapidly, almost explosively. The radiation from the central source or sources streams outward freely into the virgin neutral medium, easily ionizing the atoms in its path. But as the bubble grows larger, its expansion can slow down. The front of the ionization zone, the boundary between the ionized interior and the neutral exterior, begins to encounter denser regions of gas that have been swept up by the bubble's own growth or that were naturally denser to begin with. These dense clumps act as cosmic roadblocks. They have more hydrogen atoms per cubic meter, meaning they require more ionizing photons to be cleared. They can soak up the incoming radiation, shielding the neutral gas that lies behind them and creating intricate, finger-like shadows and neutral pillars that persist for a long time. This turns the final stages of reionization into a protracted and inefficient mop-up operation, where clearing the last 10% of the neutral hydrogen could have taken almost as long as clearing the first 90%. This patchy, inside-out nature of the process has a profound and testable consequence. It means that the universe for hundreds of millions of years was a bizarre patchwork of opposites. If you were a photon traveling through this era, your experience would have depended entirely on your location and your direction of travel. If you were emitted from a galaxy inside a large ionized bubble, you could travel for millions of light years through perfectly transparent space. But if you happened to be flying toward a remaining wall of neutral hydrogen, you would be abruptly absorbed, your journey cut short. Conversely, an observer looking back in time from a specific direction might see a distant quasar shining brightly, its light having traveled through a clear, ionized pathway. But an observer looking in a slightly different direction from the same spot might see nothing at all from that same epoch because their line of sight is blocked by a lingering, opaque cloud of neutral gas. This is not just a theoretical idea. We see evidence of this patchiness in the spectra of the most distant quasars, which sometimes show signs of being partially absorbed by neutral islands, even at times when we believe the universe was largely ionized. Understanding this complex topology is not just an academic exercise, it is the key to creating accurate computer simulations of the entire era. If our models are too simple, if they assume reionization was a smooth, uniform process, they will get the answers wrong. They will miscalculate how quickly the universe transitioned, how the intergalactic medium was heated, and how the light from the first galaxies was processed on its long journey to our telescopes. Modern simulations strive to replicate this bubble-driven reality. They start with the dark matter cosmic web, populate it with realistic galaxies based on the latest James Webb Telescope data, and then let the physics play out, watching as virtual ionizing photons flood out of galaxies and carve their way through the clumpy neutral hydrogen. The goal is to produce a simulated universe whose statistical properties, the average bubble size at different times, The distribution of those bubbles, the timing of the final overlap, match the faint, indirect clues we are gathering from real observations. It is a monumental computational challenge, but it is the only way to move from a one-dimensional timeline to a full, four-dimensional understanding of this pivotal cosmic revolution, a process that was as textured and intricate as the universe it helped to create. But the light that cleared the cosmic fog was only half the story of these first stars. Their true legacy, the one that would eventually make planets and life possible, was forged in their spectacular deaths. This brings us to our 21st great mystery, the profound connection between reionization and the very first heavy elements. The same cataclysmic supernova explosions that carved escape routes for ionizing radiation were also the universe's first and most important alchemists. Inside the furious nuclear furnaces of those massive population 3 stars, and in the unimaginable violence of their final moments, the simple primordial soup of hydrogen and helium was transformed. Through nuclear fusion, these stars cooked up the first traces of carbon, oxygen, nitrogen, and iron elements that astronomers collectively call metals, the essential building blocks for everything from rocky planets to the molecules of life. The birth of these metals and their subsequent spread throughout the cosmos was not a separate event from reionization. It was deeply intertwined with it, a dual process of illumination and enrichment that forever changed the character of the universe. The journey of these first heavy elements is a tale of cosmic pollution on the grandest scale. When a first-generation star exploded as a supernova, it did more than just flash with brilliant light. It acted as a colossal cosmic sprinkler, ejecting its newly forged heavy elements out into space at nearly the speed of light. This enriched material, now mixed with the surrounding primordial hydrogen and helium, became the raw material for the next generation of stars. But this was not a gentle mixing process. The energy from these early supernovae was so immense that it could launch powerful galactic winds, hurricanes of hot gas that raced out of their host protogalaxies and into the vast intergalactic medium. These winds were the primary delivery system for the first metals, carrying them far from their stellar forges and seeding the previously pristine cosmic gas with the first traces of chemical complexity. A galaxy that had just been sterilized by supernova feedback, its star formation temporarily shut down, was simultaneously polluting its entire local region of the cosmos, ensuring that future structures would be built from enriched and therefore fundamentally different materials. This initial metal pollution had a dramatic and counterintuitive effect on the future of star formation, which in turn directly influenced the ongoing reionization process. To form a star, a cloud of gas must be able to cool down. In the pristine, metal-free environment of the very early universe, the only efficient coolant was molecular hydrogen. But molecular hydrogen is a fragile molecule, easily broken apart by the intense ultraviolet light from the first stars themselves. This made early star formation a fragile and self-limiting process. However, the introduction of even a tiny, trace amount of heavy elements changed everything. Atoms like carbon and oxygen have many more ways to radiate away heat than simple hydrogen molecules. A gas cloud enriched with these metals can cool down much more rapidly and efficiently. This more efficient cooling allows the cloud to fragment into smaller, denser clumps. Instead of forming only monstrous 200 solar mass behemoths that live fast and die young, enriched gas can form a whole spectrum of stars, including vast numbers of smaller, longer-lived stars like our Sun. This shift in the stellar population had profound implications for the timeline and nature of reionization. A universe dominated by short-lived, massive population 3 stars would have experienced reionization in a series of brilliant, localized flashes. Each massive star would have flooded its vicinity with ionizing photons for a few million years before exploding, its light then extinguished. But as metals spread, the stellar population became more diverse and stable. While individual smaller stars produce fewer ionizing photons than a single giant, they live for billions of years, providing a steady, sustained source of radiation. A galaxy filled with these smaller stars becomes a more reliable and long-lasting engine for reionization. So, the very pollution created by the first stars' deaths ultimately led to the creation of stellar populations that could power a more prolonged and pervasive clearing of the cosmic fog, transitioning the universe from an era of dramatic, short-lived fireworks to one of sustained, luminous dawn. Yet, a major mystery remains. How uniform was this initial metal enrichment? Did the first heavy elements remain locked in the dense regions near galaxies, or did they manage to permeate the entire cosmos, even the vast, empty voids? The answer to this question is crucial for understanding the character of the universe during the reionization era. If galactic winds were powerful enough to inject metals deep into the low-density intergalactic medium, then even the gas in the cosmic voids would have contained trace elements. This would have given the entire universe a metallicity floor, a baseline level of enrichment that would have affected the cooling of gas everywhere. This could have enabled star formation to occur in slightly lower density environments than previously possible, potentially allowing reionization to proceed more efficiently in the cosmic hinterlands. On the other hand, if the metals were mostly confined to the immediate vicinity of galaxies, then the vast voids would have remained truly pristine, their gas unable to cool effectively and form the faintest, most diffuse stellar systems. The pattern of metal pollution, therefore, would have directly sculpted the large-scale geography of reionization, determining which parts of the cosmic web lit up first and which remained dark. Finding the fossil evidence of this first great period of cosmic pollution is an active pursuit, with astronomers using the most sensitive spectrographs to hunt for the faint signatures of carbon and oxygen in the most distant ancient gas clouds, seeking to map the chemical landscape of the infant universe. But while stars and quasars poured forth torrents of light, another, more ghostly army was also flooding the cosmos, a relentless hail of high-energy particles known as cosmic rays. These are not rays of light, but actual physical particles, mostly protons and atomic nuclei, that have been accelerated to nearly the speed of light by the most violent events in the universe. Think of them as subatomic bullets screaming through space with energies that dwarf anything we can produce in our most powerful particle colliders on Earth. Their primary sources are the shock waves from supernova explosions and the furious environments around supermassive black holes. While we often focus on the radiant energy of starlight, this invisible barrage of kinetic energy represents a potent, alternative form of power that could have subtly shaped the environment of the reionization era, adding a fascinating and often overlooked layer of complexity to the entire process. The primary way cosmic rays could have influenced reionization is through heating. As these high-speed particles travel through the intergalactic medium, they don't just pass through unnoticed. They constantly collide with the much slower-moving protons and electrons that make up the primordial gas, transferring a tiny bit of their immense kinetic energy with each encounter. It's a process akin to stirring a cold cup of water with a red-hot metal rod. The rod transfers its heat to the water, warming it up. In the cosmic context, this gentle, pervasive heating from cosmic rays would have raised the overall temperature of the gas spread throughout the entire cosmos. This is significant because the temperature of the intergalactic gas directly affects how easily it can be ionized. Hotter gas is more energetic and agitated, making it slightly easier for incoming ultraviolet photons to knock the electrons free from their hydrogen atoms. A universe being continuously warmed by a background drizzle of cosmic rays might have been a more receptive environment for the reionization process, requiring a marginally lower investment of ionizing photons to achieve the same result. Beyond mere heating, cosmic rays could have also contributed to the ionization process itself, though in a much more limited and specialized way. A typical ultraviolet photon from a star has just enough energy to ionize a hydrogen atom. But a high-energy cosmic ray proton carries millions or even billions of times more energy. When one of these particles slams directly into a neutral hydrogen atom, the collision is so violent it doesn't just knock off an electron. It can completely shatter the atom, producing a cascade of secondary particles. These secondary particles can then go on to ionize numerous other hydrogen atoms along their path. However, this form of ionization is incredibly inefficient compared to the direct flood of ultraviolet light from stars. Cosmic rays are relatively rare compared to photons. For every single cosmic ray particle, there are trillions upon trillions of starlight photons. So, while a cosmic ray can cause a more dramatic local event, its overall contribution to the global ionizing budget was almost certainly negligible. Its real influence was likely in its ability to preheat and precondition the gas, making the job of the starlight just that little bit easier. This introduces a complex feedback loop into our models. The very supernova that were producing the ionizing photons and blowing bubbles in the galactic gas were also the primary factories for these cosmic rays. The powerful shockwaves expanding from a supernova blast are perfect natural particle accelerators, capable of boosting protons to these incredible speeds. This means that in regions of intense star formation, the interstellar medium would have been flooded with both ionizing photons and cosmic rays simultaneously. The cosmic rays, with their ability to penetrate denser gas clouds more easily than ultraviolet light, could have heated gas in regions that the starlight hadn't yet reached, perhaps even helping to evaporate small, dense clumps of neutral hydrogen from the inside out. This synergistic effect could have made star-forming galaxies slightly more efficient at clearing their immediate surroundings, potentially increasing the escape fraction of their ultraviolet radiation and allowing it to travel farther into the intergalactic void. Quantifying the exact role of cosmic rays during this epoch is one of the newest frontiers in the study of reionization. The challenge is that these ancient cosmic rays have long since dissipated, and their energy has been absorbed and lost into the general background of the universe. We cannot observe them directly from that time. Instead, cosmologists must rely on sophisticated computer simulations that incorporate the physics of cosmic ray acceleration and propagation. They run virtual universes with and without the influence of cosmic rays to see if the resulting timeline and pattern of reionization match the observational clues we have from other sources. Does including cosmic rays help resolve the photon underproduction crisis by making the process more efficient? Do they help explain the patchiness of the ionization bubbles? The answers are still emerging, but what is clear is that these silent, invisible particles represent a subtle yet pervasive force, a background hum of energy that was woven into the fabric of the cosmic dawn. They remind us that the transformation of the universe was not a simple story of light versus darkness, but a complex symphony of different energies, each playing its own distinct part in the grand orchestration of cosmic rebirth. As we've pieced together this cosmic narrative from ancient starlight and theoretical models, one humbling possibility remains: what if some of the clues we've gathered point not just to unknown astrophysical processes, but to entirely new laws of physics? This brings us to our 23rd profound mystery, the potential for reionization to reveal hints of physics beyond our current understanding. The standard model of cosmology, known as lambda cold dark matter, has been incredibly successful, describing the universe's large-scale structure and evolution with remarkable accuracy. Yet, the reionization era presents several persistent puzzles like the photon underproduction crisis and the surprising maturity of early galaxies that have led some scientists to wonder if we are seeing the faint signatures of exotic phenomena at work. While mainstream explanations remain focused on stellar and black hole physics, exploring these alternative ideas stretches our imagination, and reminds us that the universe's greatest mysteries often reside at the frontier between the known and the unknown. One of the most intriguing possibilities involves the enigmatic nature of dark matter itself. For decades, we've treated dark matter as essentially inert, a cosmic scaffolding that exerts gravity but does little else. But what if certain types of dark matter are not completely stable? Imagine a scenario where dark matter particles can occasionally decay or annihilate each other. This wouldn't be a violent explosion in the traditional sense, but a quiet, pervasive process happening throughout the cosmos. When particles of matter and antimatter annihilate, they convert their mass directly into energy, following Einstein's famous equation. If dark matter particles were to annihilate or decay, even at a very slow rate, they would release a steady background of high-energy radiation gamma rays, X-rays, and potentially even the specific ultraviolet photons needed for ionization. This would act as a universal, diffuse power source, supplementing the output from stars and quasars. It's a concept that turns the invisible dark matter halo of every galaxy, and even the dark matter filling the vast cosmic voids, into a faintly glowing contributor to reionization. This extra, pervasive source of ionizing energy could help resolve the photon budget shortfall without requiring us to find vast numbers of missing faint galaxies, offering an elegant, if speculative, solution to one of the era's central puzzles. The implications of this idea are profound because it would mean that dark matter is not just a gravitational actor but an active participant in the thermal history of the universe. This would fundamentally change our understanding of its nature. Most current searches for dark matter focus on detecting it directly in deep underground laboratories or creating it in particle colliders. But if dark matter decay or annihilation left an imprint on the reionization process, then the ancient light we are now collecting with telescopes like James Webb and the future maps from the Square Kilometre Array could become our most sensitive dark matter detectors. We would be looking for a specific pattern in the ionization history, perhaps a more uniform or earlier start to reionization than stellar sources alone can explain. The challenge, of course, is distinguishing this signal from the complex astrophysics of early galaxies. It's the ultimate cosmic detective story, trying to separate the clue left by a new form of particle physics from the overwhelming evidence of conventional astronomy. Beyond dark matter, other exotic particle interactions could have played a role. In the incredibly hot, dense environment of the very early universe, physicists propose that there may have been temporary, exotic energy fields associated with the fundamental forces of nature. As the universe expanded and cooled, these fields would have undergone phase transitions, releasing energy in a process not unlike water freezing into ice and releasing latent heat. It's conceivable that the decay of such fields, or the interactions of hypothetical particles like actions or sterile neutrinos, could have produced a burst of ionizing radiation that supplemented the later work of stars. Another fascinating, though highly speculative, idea involves primordial black holes. These are not the black holes formed from dying stars, but hypothetical tiny black holes that could have been created from the extreme density fluctuations in the first fraction of a second after the Big Bang. If they existed in large numbers, their evaporation via Hawking radiation could have provided a widespread source of high-energy particles. As these tiny black holes lost mass, they would have emitted radiation that could have contributed to heating and ionizing the gas, potentially pre-processing the intergalactic medium before the first stars ever switched on. It is crucial to approach these alternative theories with a healthy balance of open-mindedness and scientific rigor. The history of cosmology teaches us that major breakthroughs often come from carefully considering anomalies that don't fit the standard model. The discovery of dark energy itself is a perfect example. The unexpected observation that the universe's expansion is accelerating forced us to rewrite the textbooks and introduce a fundamentally new component into our cosmic inventory. The puzzles of the reionization era could be a similar catalyst, However, the scientific principle of Occam's razor, that the simplest explanation is often the best, still strongly favors astrophysical solutions. The steady discovery of more and more faint galaxies by James Webb, or new insights into the high escape fractions of early stellar populations, could very well resolve the outstanding mysteries within the existing framework of physics. The value of considering these exotic possibilities is not that they are likely to be true, but that they force us to ask deeper questions, to design more sensitive experiments, and to remain humble in the face of a cosmos that has repeatedly proven to be stranger and more wonderful than we could have ever imagined. And so we have assembled a vast and varied collection of clues from the farthest reaches of space and time. We have the deep infrared portraits of infant galaxies from James Webb, the ghostly radio whispers of primordial hydrogen from arrays hoping to detect the 21-centimeter signal, and the intricate barcode shadows of the Lyman alpha forest from optical telescopes. Each of these observations is a masterpiece of modern astronomy, a triumph of human ingenuity. Yet, in isolation, each one tells only a partial and sometimes even contradictory story. This brings us to our 24th great mystery, a challenge that is perhaps the most human of all, the art and science of cosmic synthesis. How do we weave these wildly different threads of evidence, each from a different part of the electromagnetic spectrum, into a single, seamless, and coherent narrative of the reionization era? The central puzzle is not just gathering the data, but making it all agree, forcing a unified story to emerge from a chorus of disparate voices. Think of it as a grand cosmic orchestra. You have entire sections of instruments, each playing a different part. The radio telescopes are the deep, resonant double basses, listening for the fundamental hum of the neutral hydrogen. The infrared instruments on James Webb are the brilliant, soaring violins, capturing the high, sharp notes of the first stellar light. The optical and ultraviolet telescopes studying the Lyman alpha forest are like the cellos, providing a complex, middle-range harmony that traces the structure of the cosmic web. Individually, each section is playing a beautiful and complex piece of music, but the true magic, the real symphony, only emerges when a conductor expertly blends them all together, ensuring their rhythms, melodies, and volumes are in perfect harmony. Right now, in the field of cosmology, we are in the midst of the first rehearsals, and the different sections aren't always perfectly in tune. The story told by the abundance of surprisingly bright early galaxies seen by Webb has to be reconciled with the global constraints on the ionization history set by the cosmic microwave background. The timeline suggested by the Lyman alpha forest must align with the future maps from the 21-centimeter experiments. The great synthesis is the process of finding the cosmic conductor's score, the single model of reionization that makes every instrument in our observational orchestra play in perfect sync. The difficulty arises because each observational technique probes a fundamentally different aspect of the same cosmic event, and each has its own unique blind spots and biases. Take the hunt for the first galaxies with the James Webb Space Telescope. It is an incredible census taker, but it is inherently biased toward the most luminous objects. It easily spots the brilliant, massive galaxies, the cosmic metropolises, but it struggles to see the countless faint dwarf galaxies that might have formed the true backbone of the reionizing army. Relying solely on Webb is like trying to understand the economy of an entire nation by only studying its billionaires. You get a very skewed picture of where the real productive power lies. Furthermore, Webb shows us the sources of the ionizing radiation, but it can't directly show us the effect that radiation had on its surroundings. It shows us the light bulbs, but not the shadows they cast on the receding fog. This is precisely where the 21-centimeter observations come in. They are designed to map the fog itself. By listening for the faint radio signal from neutral hydrogen, these experiments aim to create a direct, three-dimensional movie of the reionization process, showing the ionization bubbles as they grow and merge. This data is complementary in the purest sense. It doesn't care about the individual galaxies. It cares about the holes they punch in the neutral medium. The great challenge of synthesis will be to take Webb's catalog of galaxies, their numbers, brightness, and distribution, and use it to predict the precise bubble pattern that should appear in the 21-centimeter maps. If the pattern matches, we will have achieved a monumental validation of our models. But if there is a mismatch, for instance, if the bubbles are larger or appear earlier than Webb's galaxy sensors can explain, then we will know with certainty that we are missing something profound, perhaps an entire population of unseen galaxies or a more potent role for early quasars. Then there is the crucial evidence from the Lyman alpha forest, which acts as a kind of cosmic fossil record embedded in the light of distant quasars. This data gives us a crucial timeline, showing us the state of the intergalactic medium at specific moments in the past, but its story is also complex. The forest is sensitive to both the clumpiness of the gas and the intensity of the ionizing background. A sparse forest could mean the gas is highly ionized, or it could simply mean that the gas in that particular line of sight was naturally less clumpy. Weaving this thread into the tapestry requires sophisticated computer simulations that can model the growth of the cosmic web and the propagation of ionizing radiation, creating a virtual Lyman alpha forest that can be compared directly to the real one. The simulation that can simultaneously match the galaxy counts from Webb, the bubble sizes from the 21-centimeter maps, and the detailed structure of the Lyman alpha forest will be the one that we can trust to tell the true story of cosmic dawn. The ultimate goal is a self-consistent model, a unified theory of reionization where the whole is truly greater than the sum of its parts. This model would tell us not only when reionization happened, but how it happened. It would reveal the precise balance of power between massive galaxies and faint dwarfs, between starlight and quasars. It would chart the complex geometry of the ionization fronts as they expanded through the lumpy cosmic web. Most importantly, it would resolve the current tensions, like the photon underproduction crisis, by providing a complete inventory of all contributors to the ionizing budget. Achieving this synthesis is not a passive process. It is an active, iterative dialogue between observers and theorists. A new result from Webb might force a theorist to adjust their simulation to include more efficient radiation escape. A new constraint from the cosmic microwave background on the reionization timeline might guide observers to focus their searches on a specific, crucial cosmic epoch. This collaborative dance, this constant refining of our story based on the confluence of all available evidence, is the very engine of scientific discovery. It is how we move from a collection of fascinating but isolated facts to a deep, tested, and truly coherent understanding of one of the most transformative chapters in the history of our universe. Yet as the final ionization front swept through the last stubborn pockets of neutral gas, the universe's great transformation was complete, but the story of the architects themselves was far from over. This brings us to our final, sweeping mystery, one that connects the violent birth of the cosmos directly to our own celestial neighborhood, the ultimate fate of those first stars, galaxies, and black holes. We've followed their dramatic emergence, but what became of these pioneers? Were they simply the temporary scaffolding for a later universe, dismantled and absorbed, or do their ancient bones still lie at the very heart of everything we see today? Their legacy is the crucial bridge linking the cosmic dawn to the stately spiral of the Milky Way and the brilliant island cities of the modern night sky. Consider the fate of the very first stars, the colossal population 3 behemoths. As we've seen, their lives were brilliant and brief, ending in supernova explosions of unimaginable power. For the most massive of these giants, those born with several hundred times the mass of our Sun, their death was not a supernova but something even more extreme, a hypernova or a direct collapse into a black hole. In either case, the stellar body itself was utterly destroyed or vanished from the visible universe in a single, cataclysmic moment, but their material legacy lived on. The heavy elements forged in their cores and scattered by their explosive deaths became the enriched raw material for all subsequent stellar generations. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all first created in stars like these. So, in a very real physical sense, the first stars did not truly die. They disassembled and became the building blocks for the planets and life that would emerge billions of years later. Their ultimate fate was to be recycled into the fabric of the cosmos itself, including the rocky world you are standing on right now. The galaxies that hosted these first stars faced a more varied and dynamic future. The smallest and most fragile of these early dwarf galaxies, the ones that managed to form but were then sterilized by the heat of reionization or shredded by their own supernova, likely met a quiet end. Many of them, their star formation snuffed out early, simply drifted through the cosmic voids as dark, ghostly fossils, their stellar populations aging into a quiet senescence. They are the cosmic dead ends, the failed experiments of galaxy formation, but their dark matter halos, the invisible gravitational cores around which they formed, proved far more resilient. These dark matter clumps became the building blocks for larger structures. Over billions of years, through a hierarchical process of relentless merging, these small halos were gravitationally drawn together, colliding and combining to form ever larger systems. The vast, majestic spiral galaxy we call home, the Milky Way, is the product of such a history. It is a cosmic amalgamation, a galactic empire built from the cannibalized remains of hundreds, perhaps even thousands, of those first small proto-galaxies. When we look at the faint, ancient stars in the halo of our galaxy, we are likely looking at the surviving stellar citizens of those long-vanished galactic pioneers, the direct descendants of the very first structures to ever form. For the more massive early galaxies, the surprising giants spotted by the James Webb Space Telescope, the future was one of growth and dominance. These galaxies, forming in the densest knots of the cosmic web, had a powerful gravitational advantage from the start. They did not just merge with tiny dwarfs, they began to consume other substantial galaxies, growing through a series of major mergers. With each collision, vast streams of gas were funneled toward their centers, triggering intense bursts of new star formation and feeding the supermassive black holes lurking in their nuclei. These galaxies became the bright cores of what would eventually evolve into the giant elliptical galaxies we see at the centers of massive galaxy clusters today. Their stellar populations, once young and blue, aged over billions of years into the old red stars that dominate these cosmic metropolises. The most brilliant of the reionization era galaxies are likely the direct progenitors of the most massive galaxies in the universe today, their legacy one of unbroken cosmic dominance, having ruled their patches of the universe for over 13 billion years. The supermassive black holes that powered the earliest quasars have their own dramatic story of survival and transformation. The brilliant quasar phase is a temporary one, lasting only as long as there is a vast supply of gas and dust towfall onto the black hole's accretion disk. Once the nearby fuel is exhausted or blown away by the quasar's own tremendous radiation pressure, the brilliant beacon shuts off. The black hole, however, remains a dark and silent titan. It sits at the center of its host galaxy, a sleeping giant, but its gravitational influence is far from over. It continues to govern the motions of stars in the galactic core, and its presence helps stabilize the entire galactic structure. Every large galaxy we see today, including our own Milky Way, harbors one of these supermassive black holes at its heart. The one in our galaxy, known as Sagittarius A, is a quiet, modest example, but its existence is a direct link back to the violent quasar era. It is the dormant descendant of those early, brilliant monsters, a fossil from the age of reionization living quietly in our own cosmic backyard. This grand cycle of construction and destruction, of merging and growth, is the final, crucial piece that connects the cosmic dawn to our modern universe. The reionization era was not a separate, isolated chapter. It was the fiery forge in which the fundamental rules of cosmic structure were set. The feedback processes established then the way supernova regulated star formation, the way the ultraviolet background suppressed small galaxies, the way black holes and galaxies co-evolved, became the standard operating procedures for the universe for all time. The diversity of galaxies we see today, from sparkling spirals to red and dead ellipticals, is a direct result of the different paths these early structures took, shaped by their initial mass, their environment, and the timing of their formation during that first transformative billion years. So, the ultimate fate of the first structures is, in the end, our own fate. We are the legacy of that cosmic dawn. The atoms that make up our bodies, the planet we live on, and the galaxy we inhabit are all the end products of a 13 billion-year chain of events that began when the first stars switched on and flooded the universe with light. They were not lost to time, they were woven into the very fabric of the cosmos. Their story is our origin story, an epic of cosmic rebirth that stretches from the initial darkness to the brilliant, structured, and transparent universe we are now privileged to explore. The great mysteries of the reionization era are, therefore, not just about the distant past. They are about understanding our own place in the vast, evolving cosmos, and the incredible journey from the first faint glimmers of light to the conscious minds that now look back and wonder how it all began. And so we have journeyed together to the very edge of time, exploring 25 of the most profound enigmas surrounding the cosmic reionization era. From the elusive nature of the very first stars, the population 3 giants, to the shocking maturity of unexpectedly massive early galaxies seen by the James Webb Telescope. We grappled with the mystery of the primary drivers. Was it the collective starlight of countless faint galaxies or the brilliant, piercing fury of early quasars? We examined the conflicting timelines, debating whether this was a swift revolution or a slow evolution, and delved into the patchy, bubble-like nature of the process itself. We saw how the 21-centimeter signal promises a direct listen to this ancient transformation, and how dark matter's hidden hand likely built the stage upon which the entire drama unfolded. We confronted the critical puzzle of the escape fraction, how much ionizing light actually leaked out of galaxies, and the dual role of supernova, which both cleared pathways for light and shut down star formation in the smallest systems. The potential dominance of faint, unseen dwarf galaxies presented a compelling case for the power of the cosmic many over the brilliant few, while the clumpy, textured nature of the intergalactic medium dictated the uneven pace of the clearing. We explored the elegant fossil record of the Lyman Alpha Forest, the perplexing origins of supermassive black holes so early in time, and the delayed, violent second act of helium reionization. The detection challenges, from the infrared eyes of James Webb to the vast radio ears of the square-kilometer array, highlight the immense human effort to peer into this era. We considered the subtle influence of primordial magnetic fields, the cosmic accounting nightmare of the photon underproduction crisis, and the lasting legacy of reionization in suppressing the growth of small galaxies. The forensic power of spectroscopy allows us to read the script of this drama in the ancient light of galaxies, revealing the patchy, inhomogeneous nature of the process. We saw how the first heavy elements forged in stellar explosions forever changed the rules of star formation, and how a relentless hail of cosmic rays may have provided a subtle, pervasive form of heating. We even dared to venture beyond known physics, contemplating whether exotic dark matter or other new phenomena left their mark. And through it all, we faced the monumental challenge of synthesizing all this disparate evidence into a single, coherent story, connecting the ultimate fate of those first celestial structures directly to our own home in the cosmos. This was not a simple, singular event. the Cosmic Reionization Era stands as one of the most complex, chaotic, and pivotal chapters in the entire history of our universe. It was the tumultuous bridge between the smooth, hot plasma of the Big Bang and the structured, star-filled cosmos we inhabit today, a billion-year-long revolution that fundamentally altered the nature of reality itself. It was a time of immense transformation where the first structures emerged from the darkness and, through their own brilliant but often self-destructive lives, forged the transparent universe we now study. Unraveling each of these 25 mysteries is not merely an academic exercise. It is the key to completing our story, our grand narrative of how everything we see and are came to be, from the first fleeting spark to the vast cosmic web of today. The investigation is far from over. Every new observation, every deeper look into the infrared sky, every subtle signal pulled from the radio static brings us closer to understanding this cosmic dawn. So we turn the question over to you. After this journey through the deepest mysteries of space and time, which one of these puzzles captivates your imagination the most? Is it the ghostly hunt for the very first stars, the shocking discovery of unexpectedly massive infant galaxies, or the profound possibility that we are seeing hints of physics beyond our current understanding? Let us know in the comments below which mystery you would most want to see solved. And if you want to join us for more deep dives into the wonders of the universe, make sure to subscribe. The cosmos is full of secrets, and the greatest discoveries are still waiting just beyond the light of the first dawn.